A, jest Tolga, dobrze. Tolga?
No, too late. Yeah.
Okay, no, that's...
Sorry, we have to begin now. So welcome everyone. It's time to start the last day of the 12th Gaia Science workshop and the first ORP time domain workshop here in Crete. We are sitting in beautiful environment, enjoying weather, and we've enjoyed food last night and throughout this week. And people here on Zoom, they just have to enjoy the excellent talks we have. Let's just a reminder to keep your microphones muted throughout the talks, and then raise your hand if you want to ask a question. Today's chairperson is Katarzyna Kruszyńska, and I let her lead the way.
Okay. Thank you, Łukasz. Today we will start with Jerry Gilmore talking about future of time domain astronomy. Jerry, you have 25 minutes. I will give you a 5-minute warning before the end of your talk and 5 minutes for the questions.
Thank you. Hello, everybody. It's a pleasure to be part of this continuing series of events, which started long ago in the early days of Opticon and Gaia, and has proved spectacularly successful. And so what I'm going to talk about today is what comes next. So there's an awful lot happening today. There's an awful lot that has happened, and I'll briefly go through some of that. But then we have to plan for the future. And it's well known that prediction is difficult, and prediction about the future is even more difficult. But nonetheless, we just have to try. And our approach is nicely summarized in that little poem at the bottom of the page there that I hope you can read. It's going to be challenging to whatever we do, and perhaps we won't be able to do what we want to do, but we're going to be able to end up doing something, whether we like it or not. And so let's just see what we think we might be able to do and where we've come from. No, this is frozen. Oops. Now we haven't. There we go. Good. Okay, so where are we now and where did we come from? Well, Opticon started with also at the same time as RadioNet over 20 years ago. And the ambition then was to deliver EC support to develop European astronomy and deliver access and improvement to the observing facility. Unmute myself. It says here, unmute myself. Don't do that. Don't do that.
Right, does that work?
You have to mute yourself.
Lost the screen.
Should I move Jerry?
Got it at last. Okay. Sorry, it said to unmute, and that was a mistake. Right. So carrying on. Sorry. So we started 20 years ago, and in those days times were very different indeed, and it's worth perhaps remembering that. This was even more than pre-COVID. When we started, neither the United Kingdom nor Spain was part of ESO. There was actually a serious competition in Europe as to whether or not ESO was going to become the dominant astronomy organization, or whether other partnerships would become equally significant. And one of the ambitions of Opticon was to bring together European astronomy into a single thing of European astronomy. And that's been achieved, not just by us, but by European astronomy came together rather well over the last 20 years. So both Opticon and RadioNet rapidly developed into what were called Integrated Infrastructure Initiatives, I3. And these were a very clever idea from the EC. in that there were three parts, as the name would suggest. There were three parts to the program. So there was a program of community development through networking, of technology development for future instrumentation to enhance the quality and performance of the facilities, and also access to the facilities as they are at any given time. And so we were building a community. We were providing access to facilities that people previously didn't have access to, and so therefore enhancing the scientific quality of Europe and also planning for the future. That was the Opticon side of it. And for RadioNet, which did the same sort of thing, but for them, TNA support has always been a much bigger part of the budget, and it still is. And it is organised at a facility level. Whereas in Opticon, we've developed a dedicated common TAC called a CTAC, and all the EC-funded allocation time is put into that pool and allocated in that pool through its own independent peer review system. And this system is very effective, and it works. It works very well. It doesn't work as well as it might, and that's one of the things I'll come to. We could do even better. But it's interesting also to look back. I'm not going to read the whole of this text. This is the situation as it was for the previous US National Academy Review. The new one came out this week, as you know. And the top line there was basically the introduction to the US saying, we are no longer competitive with Europe. Now, for the US National Academy to say things like that is quite a statement. But nonetheless, they did. And then they went on to explain why. And they said the structure is basically the ESO is stable, and so it can plan in the long term for big, expensive things. But the rest of and this is the important point for us, the rest of the community maximised its combined resources by having a strong network of partnerships for instrument development and small and medium telescope operations, with ESO focusing on the big things, and in particular the ELT. Now that's Opticon we're talking about there. It was Opticon that was providing this network of partnerships for instrument development. So Opticon built about a third of the sphere spectropolarimeter that it mentions up there through our R&D program, as well as other things. And Opticon promoted, and in fact was the initiator of what is now the EELT. And that I personally presented the ELT for approval by the ESFRI program. And so it's a reminder to you that a community can have its ambitions delivered, even very grand ambitions. It pays to think about what you'd really like to have, put the work into making a case for it, and then you can get it. And so that's what your future is now as well. And so that's the history of where we've come from, and an example of what we can do. Here is the same thing, just spelled out in a bit of detail, so you can show not only the scale of the partnership, but the scale of the budgets that were involved. It's a non-trivial amount of money, and it's been stable over the 20 years. The key is that it's been a mix of funding agencies, which actually have the government funding and the authority to approve things, the hardware groups, the observatories, the people who actually do the work on the ground, and industry. And all of that is necessary to bring the whole thing together. With just very little progress is made by individuals just acting on their own. So as we know, it's the difference between a herd of sheep and a bunch of cats. So the other part of this key part of the legacy is, where does time domain astronomy come into this? And this started about 8 years ago inside Opticon, is that we had a tradition of setting up networks. And the first of those was in software that was set up at meeting number 1, and ultraviolet astronomy and solar astronomy and interferometry. And each of ultraviolet astronomy and solar astronomy was funded to produce a roadmap for their own future development, and then they went off and became standalone communities. So we just set them up. And solar astronomy is now its own infrastructure network. UV astronomy eventually ended up getting a satellite, which is what they wanted. Then there's an organisation called European Interferometry Initiative, which is a sort of mini Opticon across Europe, which has largely developed the VLTI capabilities. and that continues, and they are still part of the ORP. Then there's the adaptive optics community. That's a big thing that's Europe is now global leader in. But also you'll see in there time domain astronomy. And the issue that you have to decide for yourselves is, do you wish to behave like solar astronomy and spin out and become your own structure in your own right? Or do you wish to carry on like the European Interferometry Initiative and be, although being self-managing, sitting inside a funding umbrella that gives you some resources? So that's a question we'll come back to, but that's what you have to do. And then further down there are examples of the long-term projects and the technology development programs that we also supported. And at the bottom is this important thing about training schools and telescope access. So here's an example of that development. This is the software history. This is a slide built by the people from Strasbourg who do these things, and you see there they start with Opticon funding and EC funding and strategy back before the year 2000, and then they have a map of how they developed. And this was part of one of their proposals, getting a project called Asterix, which they got, and it's now finished. But you can see how the ability to have some continuity through the middle, a stable structure, allowed that community to develop as it wished to develop. So they were not constrained in any way, they were just given an opportunity by sitting inside a structure. And this is a role model for how it may well be that time domain astronomy across Europe wishes to develop, assuming there is such a single thing as time domain astronomy. Here, of course, is a reminder of what you can do if your ambitions are large. And this thing is, of course, underway. And that picture on the right is the cover of the first original mini proposal for building a proposal that eventually turned into this real piece of metal that's being built. So the networking side of this is what you are doing now. Again, there's a list there, but in red in the middle, there's the time domain astronomy. That was a network under Opticon that just finished a couple of months ago, led by Lukash. And that was picked up by us a decade ago and said, this is obviously a field of the future. This is where we need to have an opportunity for people to start planning what they want to do and building a community and actually starting to deliver. And so that's where today came from. It's the background to that. And what's just finished, you can see here inside this Opticon package map. So you can see down the bottom left, this time domain astronomy. It didn't require a lot of money, but that small amount of money had a very strong impact because a bunch of clever, hardworking people used it to develop what is now this impressive package and community that you have. And down the bottom right, you can see transnational access, and that's a part of time domain astronomy that hasn't been talked about this week and should have been talked about much more, because you get 2 bites of the cherry. You're not only this time domain astronomy network with BH-TOM and the small telescopes, but a very large fraction, about a third, of all the funds distributed through this yellow box down here in transnational access has also gone into time domain astronomy. And this is time domain astronomy using the 4-meter telescopes and the big facilities and Las Cumbres, the international facilities. And the pressure or the involvement of the time domain community in that program is decreasing. And I think that's very surprising because the whole subject is increasing. And perhaps a little bit of rebalancing or an extra new initiative or something is required. So this is a little more detail on the access that went through that, so through the program we're just wrapping up right now. And so just right down the bottom there, this time domain astronomy community development, it was a relatively small thing. The big thing are the top 2 red bits, which are the TNA access to the 4-meter class telescopes and the bigger ones too. And the new system I'll come to in a minute, it's got even 8-meter telescopes that you can have large access to. for no cost. And so the ambition that you can see there was continue and expand the smaller and robotic facilities with transient follow-ups as the scientific focus, and that's been a spectacular success, as we've all been hearing all week. It's been a joy to see what's come out of this, and is still coming out of this. And then there was the ambition to follow up by actually being able to look at the histories of objects that you're looking at, rather than just treating the transient moment of discovery point as the only information available. And you can see some of the other things we've done there as well, like interferometry, VLTI, and adaptive optics, and so on. But this is where today has come from, but it's got a little bit out of balance. So now we move on to where we are now in the future, and that's this program called ORP. I believe you had a talk about it earlier in this week from Aga, and as I've listed at the bottom, the people here is Aga is the board chair. Vasilis Charmandaris, our local host, is the board deputy chair. Gudrun, who's over behind me, is a member of the executive management team, and Vukash is the time domain work package lead. So there's a very active leadership roles in ORP. But you can see what ORP is. It's very different indeed than anything we've done before. Well, it's closer to the original Opticon 1 than anything else, because the EC changed the rules. They wrote the rules for what is now Horizon Europe and this last part of H2020 before COVID, and at a time where Europe's big challenge was unemployment in young people. And so they switched their focus from providing access to facilities and enhancing facilities to actually getting some value from those facilities and trying to create jobs. So the EU's vision of a facility is really an industrial user going to a synchrotron and testing out some product which is going to be turned into a company or something that you can buy. Of course, we do basic science, which barely fits into their perception at all. So basic science without short-term commercial benefits requires a special case to argue for it. Now, in fact, there are such cases. Opticon has had several spin-out companies which are hugely successful, one famous one being First-Light Imaging, and I've seen various references to their cameras at various times. That was a byproduct of an early Opticon work package. And you're going to get Andreas talking about VPH gratings. You know, that's a classic case where we ought to be setting up a small company to provide this technology to Europe in years to come. So there are these practical applications. And it's worth your while thinking about anything you can do in your own communities that provide these practical hits, because that's what the EC want to justify, that's what politicians want to justify continuing to fund basic science. Clearly training state-of-the-art computer scientists, which is what you all are, is a social good, because many of you will end up working at least part-time in the real world rather than academia. And that's good for the real world, because your taxes will then pay for the rest of us who aren't in the real world. But this is the situation we're now in with ORP. We're having to re-argue the case for what we have done so successfully over the last 20 years in a context in which the world's gone crazy with COVID, but there is still this huge problem of systemic underemployment among young people in parts of Europe, particularly Central and Southern Europe. So what are we doing inside ORP? Well, I'm not going to talk about this. This is what you've been talking about all week. We have this work package led by Vukash, who never resists the opportunity to try and get me to improve my pronunciation of his name, even though I haven't even come close to starting on practicing his second name yet. I'll leave that for a future challenge. So I'm not going to talk about this because this is Black Hole Tom and what you've all been doing. You all know about that. So what's the other part of the time domain astronomy that is available right now? And that's the CTAC system. So here's a map of the time domain activities that are available for you. Okay, there's an open call every 6 months, and it includes things like overrides, monitoring, alerts. These aren't just standard single packages you can put in. I want to have available some block of time because I suspect that something interesting is going to happen sometime in the next 6 months, and I'll tell you when it happens. There are a lot of proposals like that. And then there's also monitoring stuff. And so you can see among the facilities listed in here are ones you all use, including Las Cumbres, Observatory, various robotic telescopes. But in particular, I'd like to emphasize the one in the middle at the bottom there, that's SALT. Now, SALT is the biggest telescope in the Southern Hemisphere, and it is available. And remarkably few time domain proposals are being put into SALT, even though SALT is ideal, because it's a Q-observed, service observing program. You just put your source in, and you get excellent quality data because it's a big telescope and a good site with good instruments. So I do exhort you as a community to think a little more ambitiously about what you're doing. Getting lots of light curves on small telescopes is critical and is exciting and it's crucial, but if you want spectra of faint things, you can get them just by asking. Okay? And a lot of your objects, although they're very bright at times, they're not bright all the time, or they are potentially changing dramatically, and so you need a lot of data. And so ask for those data points or you won't get them. There's another thing that ORP is working on, which is the idea of multi-wavelength proposals. What we are going to do, it's underway, is develop a system where you can put a group of people, probably it would take, can put in a single proposal to get access to data, not only on optical telescopes or near-infrared telescopes, but also the whole suite of radio domain, right through from sub-millimeter right through down to LOFAR. And it will be possible to put in a single proposal covering the whole suite of wavelengths, from the meter wavelengths right up to the near ultraviolet. And this is completely new. It's never been done before. And being a new thing, it's going to need some clever, challenging proposals so that we can design the system around those proposals.
5 minutes.
Yep, it's okay. It's only one more slide, I think. So time domain astronomy is a perfect early test case for that, because you get things where the natural timescales in the radio are quite different than they are in the optical. But doing real-time transients with VLBI is probably technically impossible, but nonetheless doing precision mapping comes up naturally to do that. So do think about these opportunities. And then there's some questions that we would value feedback from you. So ORP has a strategic challenge. The EC has asked us to come up with some models for the future. And they said, well, if you don't like what we've told you you can have now, and we told them we didn't like it, and they said, come up with something better. And so what we have to do is re-justify, basically, our funding support model. And so a question for which I need responses from you and your communities is particularly that one in the middle. What would happen if we turned off the money? If there was nothing to follow ORP? Would you survive as a community? Would you be able to manage? Do you really need the EC money? Or would the consequences be disastrous? And if the consequences are bad, then tell us, and we can write the case to the EC to not let that happen. They will give us the money, but we need to know that individuals, young people in diverse communities, are actually dependent on this stuff. And if we don't have the resource, real individuals will lose their opportunities for their careers. So I can't tell the EC that unless you tell me. So finally, last slide, some questions I will leave with you. What can we do better? We can always do things better. So tell us what you'd like and don't like about the system. Don't just tolerate it. Give us feedback. Negative feedback is even more value than positive feedback. In particular, I do not understand why people are not asking for the best facility we're offering. So think about it and do it. Then similarly, support and community development. So far, you've done incredibly well because you have a complete hero in Vukash doing all the work and the leadership for you. Now, what happens if Vukash gets tired of this and decides to do something else? What if he becomes rector of Warsaw University or something? You can imagine that. You don't get the haircut, but otherwise he'd be fine. So how robust is what you are doing? You don't let yourself get into a situation of a single point failure. Don't let ORP be your single point failure, and don't let anything else be the single point failure. So tell us what you need, tell us what you like. And similarly, just as a sort of throwaway aside, you do transient astronomy, you must be discovering satellites whistling through all the time. So if you have any real examples of problems caused, let us know. So I will stop there and leave this slide up, if I may, so that you can answer the questions. Thank you.
Thank you very much, Harry. We have a couple of minutes for questions, so if anyone has questions here, I don't see anything on chat. Okay,
if I may, so thanks, Jerry, for all these kind of words. Regarding the transnational access and time domain aspect, this has been always an issue. When we started it, I remember the directors forum, they were scratching their heads. How are we going to fit in our fixed schedules? We think semesters, we don't think, TRO, we don't think monitoring. So this is kind of orthogonal to the traditional way of planning telescope time. I think this is partially still the issue. We haven't sorted it out. And then regarding the proposals, we ourselves, and Pavel was leading this, we have applied for SOLVE last time, we've applied this time, and we were somewhat unsuccessful. So I don't know, there's definitely work to be done. I agree. Yeah,
well, on that last point, there were 2 applications for time domain astronomy on SOLVE out of a total of 65 this time around. Right. Just statistically, that's not going to get you very far. You have to try harder.
And then you asked about what would be our situation if there's no EC money. First of all, we will not get free lunches like we get here. So people would not be willing to come to conferences like this. I think this is very attractive to come and meet, and there is not much money needed. People. We can also we do support people of coming. So I think the community meeting, the community spirit would definitely suffer, and there will be less opportunities to meet. And actually, after this gap we had of 2 years of not meeting, not seeing each other in person, I really appreciate that we can meet again. This is a very different story. We can do way more. Coffee breaks, lunches, dinners. We've talked, and it triggers discussions, and we have ideas. We were stagnant for the last 2 years, and thanks to meetings like this, which are directly supported by the EC money, we can move forward. That's the point. Right?
That's a very, very strong example. Thank you, Vikash. We'll make sure we emphasize that, and particularly for young people. It's okay if you all know each other anyway, you can have a Zoom, but if you've never actually physically met someone, don't know what they're like in 3 dimensions. I met a PhD student I supervised for the first time in 18 months. Now I know how he's much taller than I thought.
Okay, one short question from Vitas. Please come closer.
Yesterday I talked to my colleague. He's professor of sub-millimeter astronomy at Caltech, but now he's the head of optical observatories department, Jonas Mudzinas. So he said he wants to collaborate with us, but he asked from us to bring the idea what we are looking for, and he said, I'm in your responsibility, and I could manage other US observatories as well as Caltech.
Okay, yeah, that's a very good point indeed. So perhaps the lesson from that is that we should repeat what we did when we started this time domain astronomy and have a workshop, a real workshop, which is just designed to throw around ideas, covering the multi-wavelengths. A dedicated, come along, toss out your ideas and build partnerships. I think we'll make a note of that. So thank you very much. That's a very good reminder of how we have to proceed. Yeah, we have to learn to speak each other's language.
Simon, you're raising your hand. Please ask your question.
Hi,
Simon?
finally unmute. Yes, sorry, I lost my mute button. Thank you, that was a really good insight. I think this network solved the photometry problem very nicely. And I haven't seen better access to photometric measurements from any other team in the world using all the resources. So that's fantastic. The weakness at the moment, as I see it, is the spectroscopic follow-up. And that's where Łukasz has been struggling to get salt time. And I don't know how to improve that, but that's where we need to put more energy and collaborate better. We had two fantastic examples of where 4 to 8 meter class spectroscopy is needed and is doing a wonderful job yesterday with the eclipsing dwarf novae follow-up, which was very, it's a field that we need to spend and invest in heavily because it gives us real masses and radii of these objects. And the other thing that was really strong was Adam's talk on the novae that Gaia is contributing to the discovery of these new novae. And again, spectroscopic follow-up is really required for these. I see Michel's hands up. He's going to say, and AGN, obviously. Thank you.
Okay. Please move any other questions either to chat or possibly to Zoom. And we have to move on with our session. Next speaker is Andrea Bianco. Andrea, the floor is yours. You have 12 minutes. I will give you 10-minute warning, so you will have 2 minutes after that.
Okay, thank you very much. And thank you, Łukasz, and the organizing committee to allow me to present this activity related to the VPHs, to the dispersing elements we are doing in the framework of ORP program. And as let me see if I can, okay, as Jerry nicely introduced, the ORP activity and large program has also some work packages related to the developing of technologies, and in particular, we are in the work package 4, the striving for excellence, and we have this activity, optimizing dispersing elements, and in particular volume phase holographic ratings, to develop and to improve the observing capabilities of the facilities available to the pilot community. So also for the time domain astronomy world. And so the idea is to design and develop such dispersing elements and making possible to improve the observing capabilities, especially for small and medium facilities. And we work with VPHs that came into the astronomical world at the end of the 90s. And they became, in the first 10, 20 years of this century, the key elements, dispersing elements of many big facilities, as you can see in this table by Kaiser Optics, and mainly as a main dispersing element for spectrograph, sometimes also as a cross disperser. And actually, this year, Kaiser Optics, which was the leader for the production of this element, just discontinued the production. And so it's quite an issue for the astronomical communities. And why the VPHs are so interesting and important, they have a very large diffraction efficiency, that we can have also large dispersion and with high efficiency, so we can reach quite large resolution, and can be make small or large depending on the writing facilities. They are very simple. You have a thin layer of an active materials where you write or transfer a periodic modulation of the refractive index. And what is really important is the diffraction efficiency of this gratings, which basically depends on the thickness of the film and the refractive index modulation. And we are, of course, interested not only on the peak efficiency, in this case, the 90%, but also on the bandwidth, because, of course, this is another key feature in the dispersing element, especially for the astronomical spectrograph. And as you can see here, we can tune the two parameters, thickness and the refractive index modulation, just to achieve the required bandwidth in the spectral range of interest with a decent efficiency. So we can predict the efficiency. We have very nice materials, holographic materials, with a collaboration with Covestro, a German company, and they are very simple to handle, since they are basically similar to the protective layer of smartphones and tablets. We have writing facility here in Italy at the Astronomical Observatory, and we can write gratings up to 20 centimeters in diameter, in a very large line density range, and going from the UV up to the K band. Here, I mean, there are some absorption issues, and we developed in the framework of Opticon, especially in the H2020 program, a detailed production step to have a reliable path to follow, and going from the design phase to a good grating that we can mount on the observing facility. And these are some examples of the gratings we produce. These were the last gratings for the Opticon. Very nice 20 centimeter gratings for with a good quality. And actually, our VPHs are already mounted in some facilities that also belongs to the TDA network, and the Asiago Telescope in Loiano, and the Canary Islands on the Notte Telescope, and the TNG. And basically, these are the wavelength range and the resolutions that are covered by the dispersing elements we have at the moment, or based on our VPHs. And they are working, they have been working for at least 5 years. So they are reliable devices. I show here some examples of what we did and the impact we had on the facilities, on the spectrograph. In this case, we developed this grism for the AFOSC spectrograph, and this is the comparison of the spectrum of a same standard star with the previous ruled grating they have, and the new VPHs we produced, and you see that the improvement in the throughput was really important. And so this was the first idea, just to improve the signal we can have, making the same device with the same resolving power, spectral range, and so on. Then we moved on also on non-conventional devices. In this case, is a grating for the Dolores spectrograph at the TNG that works in 2 diffraction orders to cover in one shot a spectral range from 0.35 to up to 1 micron. So you exploit the 2 orders, and you have this is the spectrum of the CCD, the first order and the second order. You can combine and have in one exposure a very wide spectral range. And now this grating is available for the observation. And on the same or similar idea, we also produced a stack of different gratings, again to cover with a certain resolution, wide spectral range. This was an example in the Opticon framework where we developed this 3 grating stack going from Y to H band. Okay, so we were able to have a very nice spectrograph with a single element that cover with a good efficiency this spectral range. And this is the spectra we had. So we have many possibilities with VPHs. So in the ORP program, we have to support, we would like to support the facilities. We have, with this path, we have a call for proposal. Then we have a preliminary feasibility study. Then we evaluate the proposal and select them. Then we design and manufacture the elements, and then ready to be commissioned and available on the telescope. This was the call for proposal we had the last September. So we have the details of the device you would like to have, and also the scientific targets for the dispersing elements you need. And actually, as I mentioned, the first call was in September this year, and it closed in October. We have 5 proposals submitted. Okay, we are now performing the preliminary feasibility study, and we are going by the end of this month to select 2 or 3 of them and start with the design phase. We hope to have the devices ready in about 6 months, okay, and so ready to be delivered to the facilities. And of course, we are available also for the commissioning or for the support or for the mounting and use of the elements. And then we have to decide for a second call, okay, maybe in 1 year we could have a second one. Also, it will depend on the steps if we can achieve the expected timeline, and we can deliver the expected ratings. And so I think to conclude that yes, VPH is yes.
No, it's okay. Okay, go on.
Okay, VPH can easily improve the performances of astronomical spectrograph, and we can address most of the requirements for visible and near-infrared spectral region. I think it's crucial to define the scientific requirements with clear scientific goals, and then allows us to design the dispersing elements. Okay. And I think it's really useful to discuss the possibility to use the non-conventional devices as the multi-order or a grating stack to really maximize the effect of this improvement. And of course, we are available for supporting and discuss about the gratings related to the astronomical facilities. And thank you for your attention. And I'm available for the questions.
Okay, thank you very much, Andrea. Do we have any questions for Andrea? Łukasz?
Very nice. Can I ask what's the rough cost, if you can tell us, of course, of such one unit?
Okay, regarding the costs, it depends of course, in the ORP program, we have covered the production costs and the designing costs of the elements. So for the selected proposals, basically the target facility doesn't have to support the cost of the production. Of course, if there is the need of for the commissioning and specific, for example, specific situations of the creating with specific materials, it can be possible that contribution is needed, but it means for a size of in the range of 1 or 2 inches, 20 to 50 millimeters diffraction elements, the total cost just for the production and optical elements is just a few thousand euros. So in this, but in the framework of ORP, of course we have covered these expenses. Keep in mind that if the size increases, the cost is not linear with the size, but basically it goes more with the area.
Okay,
thank you. Now, if you have any other questions, please ask them on chat or on Slack. And now we move on to Stephen Potter. Stephen, the floor is yours. You have 12 minutes. I will give you a 2-minute warning.
Right, thank you. Just get going here, share screen. And okay, am I good to go?
Yes.
Great, thanks very much. Well, first of all, I'd just like to thank the organizers for giving me this opportunity to speak to you all today. I really appreciate it. My name's Stephen Potter. I'm from the South African Astronomical Observatory in Cape Town, South Africa. I also hold a visitor's position at the University of Johannesburg. So today I'd like to talk to you about a program or project at the observatory called the Intelligent Observatory. And this is in fact a combined project of the SAO and also the South African Radio Astronomy Observatory, both of which are national facilities of South Africa. So here's an outline of my talk. I'll just, to set the scene, I'll just briefly, very quickly give you an idea of what telescope facilities we have in South Africa. And then I'll move on to describing what the Intelligent Observatory is all about. It's why, what, how, what its current status is, and what's coming soon. So to move on to the telescopes. So here's 3 photographs of our 3 workhorse telescopes that we have based at our observance station in Sutherland. Basically, there's 2 1-meter telescopes. The one on the left is about 50 years old. The one in the middle is about 5 years old. Telescope on the right is our 1.9-meter telescope, and that's in fact over 70 years old. But the important thing is all 3 telescopes are equipped with modern-day control technologies and modern-day instrumentation as well. So the only thing really that you need to know is the apertures. And between the 3 telescopes, we have instruments that are capable of spectroscopy, polarimetry, and imaging. And one particular area of expertise at the observatory is, in fact, high-speed photometry, high-speed imaging. And of course, in Sutherland as well, we also host, maintain, and operate the Southern African Large Telescope. This telescope is funded by a consortium of organizations, including in South Africa, some in the US, and some in Europe and in India. And this is a Q-scheduled service observing telescope and is capable of imaging, spectroscopy, and polarimetry, and various combinations of those. And as Jerry said earlier as well, we also have the ability of high speed modes in observations in these modes. But in addition to these telescopes, you can see this photograph below with the plateau in Sutherland. We also host a lot of other facilities. Some facilities are joint partnerships between South Africa and other countries. So for example, the telescope on the far left is an infrared 1.4 meter telescope that we operate in partnership with Japan. Moving over to the right, there's this optical telescope called Meerlicht. It's a partnership between South Africa, University of Cape Town, and institutes in Holland and the UK. And then we have other telescopes in partnerships with, say, Germany, Korea, and Russia, and Poland, just to name a few off the top of my head. And of course, these three telescopes in the foreground here, these are 3 1-meter telescopes, are part of the LCO World Network. And because we either host or partly operate these telescopes, we have time on all of these telescopes. Okay, so what's the Intelligent Observatory all about? So it's always good to start with why this particular project. And the answer is we want to be able to better serve the community, our users, you, the astronomers. We want to be able to allow you to submit proposals at any time, rather than the traditional way through trimesters or semesters, and thereby enabling you to do science on any time scale, rather than, for example, being restricted to the traditional 1-week blocks that we operate on our telescopes. We want to give you the ability to either go to Sutherland and observe on the telescopes, or observe from our headquarters in Cape Town, or in fact observe remotely from anywhere in the world. And therefore, similarly allow you to observe manually or use queue scheduling or service type observing. Also, we want to do this because we want our facilities to respond to alerts or other types of computer generated requests, and also to enhance our national and international partnerships. So what exactly is the Intelligent Observatory project? Well, the vision is that we want all the telescopes integrated into a central intelligent observatory. So all of these facilities are all kind of operated in their own independent way, but because we have access to all of them, we want to present this as a whole observatory, and therefore be able to better coordinate science across all the telescopes in Sutherland, particularly in this so-called era of multi-messenger astronomy. And so this, and I guess this is the program that's advancing the SAO into the so-called 4th industrial revolution by building on these new technologies. So how are we doing this? So we've identified kind of 4 work streams that list of how we're going to meet this vision. The first of which is we're going to have to upgrade our hardware and software, particularly of our workhorse telescopes, so that they will be able to, for example, be more automated rather than fully manually controlled. We also need to look at our data science software. So in addition to giving kind of to the traditional recipes for reducing and analyzing data, we'd want to introduce more pipeline and quick look type software as well for all our instruments and telescopes. And that then will enable us to, for example, do automatic classification or photometry, which then would maybe lead on to automatic triggering of further observations on one of the other telescopes, perhaps. And so then a third work stream then would be consistent of more software, but maybe along the lines of perhaps artificial intelligence, but certainly kind of taking advantage of machine learning and the internet, so that we can prioritize and manage and organize alerts, especially from LSST in the future, but particularly also because of Meerkat and SKA, which are obviously also based in Southern Africa, and obviously the gravitational wave facilities as well. And also the fourth work stream is, in order to meet this vision, we're going to have to remanage the way that we do astronomy operations in Sutherland. And this means readdressing how we allocate time, how we organize time allocation committees, how we're going to manage alerts and allow you to submit proposals at any time. So in fact, we started this project almost 2 years ago now. So I'll give you a current status. So at the beginning of the program, if you wanted to use our facilities in Sutherland, particularly the workhorse telescopes, then you as an observer would have to apply for time through the traditional trimester call for proposals. And if you were awarded time, you would get awarded time in 1 week blocks, and you would have to travel to South Africa and to Sutherland and manually operate these telescopes yourselves. Of course, there are other facilities as well that have other ways of using time, like the LCO network, for example, but this is how you would use our telescopes. Now we're almost 2 years into the program. Then in fact, you no longer need to go to Sutherland. Wherever you are in the world, you can now access not only our new 1 meter telescope through whatever is your favorite web browser, but we've also upgraded our older 50-year-old 1 meter telescope that is now also fully remotely operable through your favorite web browser. And in fact, our 70-year-old 1.9 meter telescope has now been upgraded to the extent that you can also remotely access and observe this telescope through these telescopes. And by what I mean by remote observing, I mean that these telescopes will be completely unmanned. So we've upgraded it such that you can connect to your web browser, power up, open the domes, do your observations, close the domes, and power down without anyone having to go into the domes. So that's where we are right now. But the important thing about these upgrades is not necessarily that it now enables you to do remote observing. The important thing is now that these telescopes are ready to be operated programmatically. So they're ready to be managed by software rather than people. So that leads me on to the final part of my presentation, is where is the vision for the Intelligent Observatory now going, given the current status. So in addition to allowing you, the community, to remotely operate the telescopes, we now want to be in a situation where we can allow non-humans to operate the telescopes. So for example, we're going to be ready for the inflood of alerts from the LSST program. We want to be ready to automatically respond to gravitational wave alerts, and also, of course, the spaceborne satellites, the Gaia mission, for example, but also the X-ray and gamma ray missions. But in addition to that, we would want to be in a position where our telescopes in Sutherland are in a position to automatically talk to each other. So one example, I pointed to this telescope earlier. This is the Meerlicht 0.6 meter optical telescope. And what this does, this telescope is automatically slaved to the Meerkat radio observatory. So that you can imagine, if a particularly interesting radio transient is detected by Meerkat in the radio wavelengths, and then simultaneously, if the Meerkat telescope observes and detects an optical counterpart, then with some automated data reductions, etc., this telescope would then automatically analyze that data, ascertain its brightness, etc., and then send an appropriate alert to one of the other telescopes, for example, SALT, to maybe do follow-up spectropolarimetry, or maybe one of the 1 meter telescopes to follow the radio transient over longer periods of time for longer term photometric monitoring, for example. So in order to make all that happen, the next phase now that we're moving into is that we need to develop a central control system. So this will be the system that we need to develop that does everything that I just described. And so the central control system was basically going to redefine how we do astronomy operations at the SAO. It's going to consist of many more types of software algorithms, perhaps intelligent, some forms of artificial intelligence to prioritize observations, requests and alerts, etc. We're going to have to move away from manual observing and start incorporating queue schedulers. We're going to have to define new systems to sift and prioritize through the various alert systems. And of course, I've already said we're going to have to do some real-time data analysis. But we're not going to invent all of this from scratch. In particular, the last three items, we're going to have to redefine how we do proposal management, observation management, and data management. But as we heard earlier this week, the Las Cumbres Observatory have already made their observatory control system freely available. And we're currently looking at how we can adapt that to our observatory, so at least that then handles those last three items. And many of these other items as well will make use of, say, the TOMS toolkit. Okay, so I've coming to the end of my talk. If you'd like to find out more about the Intelligent Observatory, there was an article written in Physics Today earlier this year, with particular emphasis on transient science. Otherwise, we have a website where you can find out more information, or please feel free to email me if you'd like to know more or somehow get involved. Okay, thank you very much for listening.
Thank you very much, Stephen. We are slightly short on time, so please ask your questions on chat on Zoom. And we move on now to Doug Arnold. Doug, you have 15 minutes. 12 minutes. I will give you a warning, 2-minute warning.
Okay, thank you. I'll share my screen. Right, okay. It's fantastic to be talking and really inspiring to see kind of how many people are dealing with many facilities and joining those all together and actually doing it. What I'm talking about is a single facility and more plans, but it's on behalf of a group of people here that are in the software team. So what I'm just going to do is give a little bit of an introduction to the team, where we are.
Excuse me.
Yeah.
Your microphone is somewhat making the sound hard to really get through. Do you have any other microphone you can try? Or?
Wait there one moment. So. Okay, so is that no good?
No, it's the same.
Okay, is that any better?
Oh yeah, that's better. Yeah.
Okay, great, perfect. That's my thing. Okay, just share screen. Right, so where are we up to? Yeah, the project and team. So I'll speak about the LT experience and how our plans for the NRT differ, because we are in a different era. So within the work package breakdown structure, work package 4 is all of the software and control of the telescope. And we've split this into 3 sub work packages. Our team is split between LJMU and our project partners at the Instituto Astrofísica de las Canarias. And at the moment, we're kind of looking at a 4-year project with 5.5 kind of staff. Rob Smith and Miguel Angel Torres, who are the managers. I kind of put down as 25% of their time dedicated as resource to this. And we're hiring a new DevOps engineer next quarter. The advert has just gone out, so please just Google New Robotic Telescope and you'll see details of that. Please pass that on. So our construction plan is to be ready for first light within 2026. So kind of, 4.5 kind of years, we'll need software systems in place for commissioning and also first semester science operations. And at the moment, we've kind of, this is our preliminary design review documentation. Our first ideas is a 3-level stack with the Science and Operations Data Center providing interfaces to the users, the robotic control system replacing any human or remote human observers, and then finally at the bottom the telescope level systems controlling the actual mechanisms and providing the astrometric coordination and all of the mirror support. Now we're going to be using, or the plan is to use a fork of the GrantCAN control system. We have good links with the GrantCAN team, and already being a segmented mirror telescope, this makes a lot of sense. So what we've been doing is looking towards the preliminary design review and making a technological demonstrator of these 3 levels, a toy model, where we've really focused not so much on the actual functionality of the different elements, but looking at technologies that we want to use and making sure that the interfaces are fit for purpose. One success of this has been in a microservices model of the robotic control system and setting up kind of a DevOps CI/CD build structure with online testing using GitHub Actions, where we create a empty container, and then that is inherited through Docker files, and then we put the service code of what that service does within the robotic control system microservice architecture into that empty container, and then we also have testing and test supports before it's being deployed, and this is working very well. But what I will focus on later is what we've done at the more top end of the kind of the stack, looking at our website offering and how we communicate with the phase 2 database, which the scheduler pulls. Our goal is to have a fully working stack with a simulated telescope. It's not very smart, but the GrantCAN control system has a simulated telescope. It follows objects through the floor. It can follow them all the way around the sky, but that doesn't matter. It provides the interfaces that we need to fully test the system and make observations in a simulated way before we have a real telescope. So this is something where I'm stepping into the lion's den a little bit. I'm not experienced in this. I wasn't around at the time, and I'm speaking about stuff that people at this meeting might have been involved in, but bear with me for this. So I think this is a uncontroversial statement that FITS is the most successful global standard within astronomy. Now, I'm not sure if I agree with it, but is FITS the only successful global standard within astronomy? And the kind of experiences that we had with the LT was very heavily based within eStar and RoboNet. It was presented at SPE in 2006, the Operating Heterogeneous Telescope Network here by Alistair Allen. And that at the very bottom used very kind of RTML and VO events, prescriptive XML markup language formats that would be shared and used across the network, where it was prescriptive in the way that you would access a resource and the responses that you'd get back. And the actual whole network was planned upon kind of the VO event flow and that. Now, eStar and RoboNet was a success. The funding stopped in 2009, and the vision of a heterogeneous telescope network kind of became, I believe, LCO. And they really have made the model work. But they're a single organization where they can control kind of the data flow around their network a bit better. Now, LCO's experience kind of when they were looking at what's become the nascent Aeon, well, it was nascent Aeon model, was a more abstract kind of observatory. And this is a fantastic talk. I highly recommend anybody who's interested in this to go to it. I'll put the link in Slack. But Eric Saunders kind of said that really we don't need specific standards for the telescopes, but to specify key interface functionalities and make those interfaces as easy as possible to use. And actually the standardization is done at a much higher level. So the Monet telescopes, for example, use RTML right at the very kind of operational level of the telescope, very low down. We want to try and keep any global standards out of our telescope, but make it as easy to plug in at a much higher level. Another example of this abstraction to higher levels is, for example, Astro Query within the AstroPy library, that brings together a huge amount of data sources with different standards for communication, but hides that from the users in a very simple API. So based on this, we've kind of got the NRT ethos and plans going forward. So just to remind you, I just wanted to highlight kind of what we've looked at the top end of the technological demonstrator and the model that we've kind of made our toy model. And I worked over the summer with Chris Rowe, a summer student, and he created a Django-based web interface to speak to my Phase 2 API. And we were testing kind of our authentication methods, and then we were testing with loads on the database. And this is kind of the structure that we created a website that speaks to a client that's part of the DevOps CI/CD model. We test the client against the API within GitHub, and then that would speak to our Flask API for speaking to Phase 2. OOP stands for Observation and Operations Portal. And in this model, we are using the client that we also supply to observers, or they can write their own client in any language because it's a REST HTTP kind of interface. So we're not having different ways into the telescope systems. There's a single point of contact, and we're using our own kind of product that we provide to give our website. And we did some kind of testing on this. We loaded the API with 30 requests per second, and then did a latency test through the website. And we did this for different database sizes, and kind of we filled the database with the number of observations that the LT has kind of done within 15 years. It was a simple query on the table. We used SQLite so that there wasn't any kind of caching, which we would have got with Postgres, which will be our production database. And we found that really the latency of 0.5 seconds for a page load for the user to show their observations out of 150,000 was actually kind of reasonable. So we do believe that this model is going to be functional. But what it allows us to do with our goals is to distribute very usable libraries, the OOP client, and then there'd be the API client.
Doug, you have 2 minutes.
Yep, fantastic. And what we're going to do is create our own website interface for users using these, but also we would create a VO events converter, for example. We'd have a lesser subscriber functionality that we might write. And then other kind of operations such as the growth marshal that uses our RTML and TOM systems and the National Schools Observatory would all be using these clients. Also, probably our spec time survey would actually be a separated app from our website and would use these. And we're hoping that we can really chase down, the key thing here is to chase down the instrument shutter close time to data being available and alerts being generated. We might use webhooks or Apache Kafka, as Lasser uses, which is a very good technology. And the key goal is that basically we would, if we were doing it today, we'll have to see in kind of 2026 what will be the best way, but Jupyter Notebooks, and the idea is that this is available to kind of master's level students to be able to submit observations to the telescope and receive confirmations of when their observations are being done and when data is ready, and to be able to kind of train them within an hour session, basically. So those are kind of our goals. We do need to also look at the observatory control system of LCO because there's a lot in there which may be applicable with helping us achieve those goals. So, yep, thank you for that. And if you've got any questions, I'll happily take them.
Yeah, thank you very much, Doug. We have time for one, maybe two short questions. Laurent? No, okay. Nothing on chat. Okay, so if we don't have any questions, but maybe they will come in a few seconds, please write them on Slack or on chat. And now we will move on to a series of short presentations. First speaker is going to be Alessia Garofalo. Alessia, you have 5 minutes.
Yes.
I will give you, sorry, you have 4 minutes, and I will give you 1 minute warning. So we'll have, so then you will have only 1 more minute.
Okay. So can I start?
Yes, yes, yes.
Okay. Hi everyone. I'm a fixed-term staff member at the INAF in Bologna, Italy. I'm here to give you a short update on the Lyanna Telescope and is using the follow-up observing campaign of a transient object detected by the Gaia Science Alert. Here I show you some technical details on the telescope that is next to Bologna, is around 37 kilometers from Bologna. The main instrument is the BFOSC, which allow us to acquire both spectra and images with a simple configuration change. And at the Bologna Lyanna Telescope, there are different kinds of activity, teaching, research, and science activities. The main research activity is linked to the space situational awareness. There are currently 5 projects linked to this topic. The aim of this project is try to track the orbits of space debris and artificial satellites, and also the orbits of minor bodies like asteroids and comets that are in the solar system, considering also the bolids, which are due to the fragments of minor bodies following in the Earth atmosphere. At this link, you can find the dedicated web page. Together with this research activity, each 6 months there is an open call at the Lyanna Telescope to get observing time. One of the long-term projects at the Lyanna Telescope is a project focused on the Gaia alerts follow-up. The name of this project is the Transients Sky with Gaia. Here the investigators from INAF and the co-investigators. The project started in 2014, and from 2014 up to now, more than 2,300 of observations for 120 targets help to classify this object using the photometric and spectroscopic data from Lyanna. Here you can see in this histogram the fact that the 60% of the Gaia alerts are accessible with the Lyanna Telescope. And here the multi-band light curve of the target Gaia 16AYE, the object that also Vukash the first day in his presentation shown. And with the Lyanna Telescope, we contribute to this multi-band light curve with more than 200 of observing points. Quite recently, in 2019, I became the PI of this project, and in 2020, with the COVID-19 outbreak, the Lyanna Telescope applied the national health-related restriction measure, and so the activity has been suspended for 2 months. So we lost the 26% of the observing night, and with the reopening in the middle of 2020, up to now, the situation is the following. All the observations are temporarily carried out remotely. So I hope that in the next future, I mean, next 6 months, the situation will improve. So while I'm keeping my, let me say, finger crossed to this improvement, I leave you with this table with the targets and the observing points that has been collected during and after the COVID-19 outbreak at the Lyanna Telescope for the Transient Sky with Gaia project. Thank you.
Very much, Alessia. Any questions?
Just a quick one from me. So Alessia, I know you've been with us for a very long time from the very beginnings, which is great. I'm wondering, because I see you show plots from the original CPCS, but are you already using black hole Tom, or are you planning to do, or if there is anything we could help?
Yes, I started to use, I just upload few observing points on the BH Tom last month, okay. So I hope to keep going to this server.
Okay, great.
Okay, so I don't see any more questions, so I think we can move on. If you have any questions, please ask them on chat or on Slack. And now I would like to invite Tolga from Istanbul University to talk. And Tolga, you have 4 minutes, and please.
Yeah, okay, thank you very much. So today I will try to kind of briefly talk about the 60 centimeter telescope that we have here in, not in Istanbul, this is where we are, but of course it's practically impossible to do any kind of real observational astronomy. So the telescope is right on the other side of the Aegean Sea, it's on Çanakkale. This is the site you can see. There are other telescopes. There's one 1.2 meter telescope here, and our 60 centimeter telescope is down there. It's a hill basically up like 500 meters above sea and so on. So this is the telescope. It's bought from Astelco some I guess in 2011 or so. So it's almost like 10-year-old telescope now. We recently tried to update it a little bit, bought a new CCD, an Andor CCD, and then we bought some STSS filters, GR and I-band filters, which improved the overall system. And finally, we actually made it so that it would be a robotic telescope. I mean, it still needs some babysitting, but it works just fine, at least for the moment. For some time, it actually really responded to Gaia alerts as well, basically scheduling every night some small exposures for each Gaia source, and then basically submitting it. This is from there. We started observations in 2019 August, but then we had some malfunctions which basically caused us to basically just wait for fixings and stuff like that. Just a few weeks ago, actually, maybe a month ago, we started testing observations, and Gaia, this 21A EFS, has been one of the sources. This is just one I downloaded from BH-Tom. We started uploading some images to there. We already have about like 3,000 images, but we don't upload all of them, just like a few images per night and so on. So hopefully we will continue in the next future to follow up all the rest of the interesting, let's say, Gaia sources. And thanks a lot.
Tolga, thank you very much. We have time for one, maybe two questions.
Well, I'll just comment that this is great to see you're improving your telescope, and as I asked Alessia as well. So if there is any, and you've been recently actually actively involved in setting up the Black Hole Tom data processing. So that's the way to go. Okay, thanks. Yeah, sure. I mean, with these small telescopes, the sustainability issue is always a problem, I guess. Like, you know, just a few weeks ago, we lost, for example, the filter wheel, and just for the chip, we had to wait for a few weeks and stuff like that. So we lose so much time, but sometimes it works just fine. So. Okay, thank you.
Okay, thank you very much. I would like to move to the next speaker. So if you have any questions, please ask them on chat or on Slack. And now I would like to invite Siegfried van Verweyke.
Yes.
Siegfried, you have 4 minutes, and you can start.
I'm sharing my screen. Okay. First, I will say a few things about our observatory, Astrolabe Iris Observatory. Astrolabe Iris is located in Wipers in the western part of Belgium. It's a public observatory which has a lot of educational activities. It grew out of the local astronomy club in the 1990s and became a public observatory with public funding from the Flemish government around the year 2000. Over the years, Over the years, we have also developed a scientific observing program. We use a 68 centimeter telescope on alt azimuth mount, and we have a CCD camera from Santa Barbara Instruments Group. Our observing team consists of 4 members.
Siegfried, you're not in full screen mode.
We don't see your full screen. We only see the PowerPoint.
You not see the full screen, why?
I think you're sharing the window of PowerPoint and not the desktop. That's
This is possible, yes. Okay.
Okay, perfect. Yes.
Okay.
Yeah, that's it.
So our observing team consists of 4 people. The observations were mainly conducted by Frankie Dubois, which is the man on the right in the image. And I am personally mostly responsible for the scientific observing program. The 2 other members, Ludwig Rogy and Steve Rau, are mainly involved in technical operations of the telescope. Over the years, we have been participating in many observing programs. You can learn about those programs if you type in my name in archive or ADS. I cannot switch my, So in 2019, we became involved in higher alerts and we started observing microlensing events. One of the first events we observed was higher 19 DKA, which is important and has been discussed several times during this workshop. It is a long-term microlensing event. Its importance is that it shows the effect of the Earth's annual parallax when it moves around the sun, which is important to determine the mass of the lens. This lensing event has been observed from many observatories, including ours, and our observations, which are indicated by crosses, have now been submitted to the Black Hole Tom. Then at the start of this year, I started collaborating with Roger Dymock, the new director from the exoplanet section of the BAA, to start and try observing and to find exoplanets using higher alerts and microlensing events. As you know, double lenses involving exoplanets can cause small deviations in the Baginski curve of a microlensing event on the timescale of a few hours up to a few days. The challenge in terms of observing cadence and in terms of observing schedule is to be able to detect these events using a network of robotic telescopes on the Earth. The picture I show is such an event from the Ugu survey, which was detected in 2005. And thanks to Gaia, we can now do this using microlensing events all over the sky. The next plot shows a line curve from the microlensing event Haya 21 DNC, which was observed by the BAA, Roger Dymock and his colleagues. They had a gap in between the official announcement of the higher alert and the start of their observations, which they have managed to observe the event quite well. Of course, in the United Kingdom and Belgium, we are limited because of the limited number of clear observing nights. And therefore, many of our observers from the Belgian working group on variable stars have turned to developing robotic telescopes instead, one of which is the Road Observatory, which was presented by Jos Hams yesterday. But there is also EI, which is the biggest facility in Europe for housing robotic telescopes in the Extremadura region in Spain. It has a lot of facilities for housing telescopes in general excellent skies and is run by a local Spanish amateur. Several of our members, including Tony van Munster, Sjoerd de Voer, and Martin van Leenhoven, have put up robotic telescopes there. The next slide shows an example of one of these. This is the Celestion Telescope operated by Tony van Munster at EI Observatory. Over the past few weeks, a new microlensing event appeared in the northern sky, which is designated Gaia 21 EFS. It is located in the constellation of Cygnus and is very well located for observers. We started to use all equipment and all observational procedures to observe this event. The plot shows the observations from Black Hole Tom, and the last time series in Astrolab IS was measured by Frankie Dubois using the NMPT. Then the robotic telescopes in EI came in the V filter with observations from Jules Dufour and Tony van Munster. And finally, we were able to cover the maximum of this event quite well. In the meantime, Gaia 21 EFS has reached its maximum magnification and is now in the declining phase of the microlensing event. So far, we have not yet detected any kind of evidence for an exoplanet perturbation, but this may happen in the near future still. Obviously, we can still improve by improving the longitudinal covariance of the network. And this is something that we will work on in the coming months. I have contacted several observers in the United States and in the BAA to participate in this project. So my final conclusions are Astrolab NMPT combined with the remote observatories from VVS is operational. One crucial point is to improve longitudinal coverage. The biggest astronomical association and its robotic telescopes will probably play an important role in this. And one of my personal thoughts is that we should also improve the speed of the alert stream, because there are some false positives associated with VE stars that masquerade as microlensing events in the early stages. So thanks for having me and organizing these events. I will leave it there for now.
Thank you very much, Siegfried. If you have any questions, please ask them on chat or on Slack. And I would like to invite the last speaker of this session, Milan Stojanovic, please. Okay, you have, yes, you have 4 minutes.
Okay, thank you. Good afternoon, everyone. So my name is Milan Stojanovic. I'm working at the Astronomical Observatory of Belgrade. Here we are a team of 2 people contributing to Gaia alerts, and we have our, let's say, mission here to improve this network that was already established. So we have established a network in, it's called Serbian-Bulgarian mini network in 2013, and we started with observations of Gaia alerts from October 2014. We have 6 telescopes in total at disposal. Now it's almost 7. I am saying almost because the new 40 centimeter telescope will come soon. And all our observations are done via, let's say, a smaller project under one bigger project. So, for example, for now, my colleague Damjanovic and Bachev from Bulgaria, they are PIs of this part of the project from 2020 to 2022. At Astronomical Station Vidojevica, we have one telescope, 1.4 meter and one 60 centimeter telescope. At Rožen, we have these 3 here. The biggest one is 2 meter, and at Belogradžić Observatory, we have another one from 60 centimeters. The biggest problem with let's say, our observations, since we cover the different locations, so we are, when we have observing time, it's almost sure that one of these observatories will have a clear night. Of course, not, it's not mandatory, but we have a bigger chance. But the biggest problem is we don't get the observing time so often. So in total, we have 2 to 3 nights per month. So between 2 and 3 nights per month, sometimes 2, sometimes 3. And with the new smaller telescope, 40 centimeter telescope, we hope that we can use this telescope almost as a dedicated, or let's say, maybe a half month of the time could be devoted to Gaia alerts. I'm not going to explain too many details. So here are all the telescopes that we use with the cameras, and here are just the camera size and the pixel size, the descriptions actually of what you can see. We have a few under Iconel camera, Flea camera, and so on. This is the biggest telescope at Vidove. It's a 1.4 meter telescope that we use. And here is the smallest one here, 40 centimeter. It's completely finished. We have just, let's say, a few more, maybe a month or something like that of a testing phase, and then it will be completely operational. These are two of three telescopes that we can use in Bulgaria. And of course, the observed objects that we covered in 2021 also covers the Gaia 19 DKE, which was very well observed by many observatories, but also some other. All the objects, all the Gaia alerts that we observed are from ASV, from a Vidovec observatory here in Serbia for this year, because we had some problems with Bulgarian part of the telescopes. They were doing some reconstructions, and so it was not always available. As you can see here, we dedicated our time mostly to these two transient objects, and we covered we created almost 350 CCD images for the 2021. And here are just some total numbers from 2014 since we started using this mini network of telescopes. In total, we uploaded 3,300 data points, images from 2014 today. And here are some, let's say, observation characteristics. The seeing is, I'm really sorry for this. The seeing is between 1 and 3 arc seconds, depending on the night. And we hope that with a smaller telescope, of course, we cannot reach magnitudes like here. For example, 2-meter Rosen telescope can reach down to 20 magnitude. We will observe brighter ones with the smaller telescope, but hopefully with much more available time for observations and for the Gaia alerts. Thank you. That's all.
Very much. So I think that concludes the last session. So if you have any questions, please ask them on Slack. Now we will have a 20-minute long coffee break. 25? 23-minute long coffee break. And speakers, please, speakers for the next sessions, please come 10 minutes earlier before the session, and so we can test if your slides are working. Łukasz, do you have any comments?
No.
Okay, so now we can go for the break.
Hi, hello.
Hello. Do you want to test your slides?
Yes, I would like to test my slides.
Okay.
Okay, I will do the full screen. Okay. Okay, can you see the slides?
Yes, yes. Could you try checking if the slides go correctly, if they change?
Mm. Oh.
Okay. Good.
Yes, it's going. It's going. Okay, great. Thanks.
Okay, great. Thank you. Is there anyone else from the speakers for the next session who want to check their test their connection? Yes, hello.
This is Rupak.
Oh, hello, Rupak.
Hello. Yeah, so may I share the screen just to check whether it is okay?
Yes, 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 yes.
Check. Can you see my screen?
Yes.
So
No, you're not in the full screen, but if that's okay with you, that's
I'm
fine.
doing. Yeah, is it now full screen now?
Okay. Yes.
So I'm
Yes.
changing my slides. It's working, right?
Yes.
Yeah.
Yes. Okay. Great. Thank you very much.
Thank you. Thank you.
Okay, can I also test it?
Yes, yes, go ahead. Siegfried, you have a raised hand on Zoom?
Yes, but this was in relation to the previous talk. It's not relevant anymore.
Okay, okay. So, so you can ask your question on the top, or
Yeah, okay.
or something. Could you unmark the hand? Thank you very much. Okay, Nada.
Okay, so puzzle. Here you can see you creating no glasses, unfortunately.
Are you sharing or not yet?
No, I have an issue with presentation wings. I forgot to
So maybe I'll can I try sharing now? Or, let's see. Oh, there we go. Oh, now I can't hear anything.
Patrick, you can go and check the slides.
All right. Oh, can I? Oh, see, can I try to share? No.
Well, we can hear you. We cannot see your screen.
Okay, is it my turn?
That's okay.
Sorry?
Okay, I guess I'm trying now. So let's see if it works.
Okay. Yes, we can see your entire screen.
Okay.
Great. Ah,
You can
perfect.
see the
Could you
slide?
change? Yeah.
Okay.
Could you change them?
Oh, change it?
Yes. Okay. Thank you very much.
Okay, great.
Good. David, have you tested your slides?
We can do now.
Okay. Ah, looks very nice. Yep. Thank you very much. Mariusz, jesteś tam? Mariusz?
No problem.
Hi, everyone. I'm going to hear you actually.
Hello.
Yeah, hello. May I test my slides?
Yes, please go ahead.
Okay. So there's sharing. Is it going okay?
Yes. Okay, and changing slides works. Great. Thank you very much.
Okay, thank you.
Right, we are about to start. Before we continue with the session, I have a small announcement to people building their telescopes or considering building or upgrading the telescopes. We have still unofficial, but we are getting towards an agreement with the Under company, Under selling the CCDs, right? So they are very happy to help us with our network, and they promised to give us some significant discounts on their cameras if we are partners of our network. So that's probably a kind of a new type of benefit of joining our network. So more details, bear with me. There will be some announcements in a couple of weeks, I guess. But this is just a preliminary announcement that there is going to be some agreement between our network and Andor company. And I'll give the floor to Kasia to lead the session.
Okay, hello everyone again. We will start now our last session, which will focus mostly on extragalactic transients. The first speaker is going to be Patrick Kelly. Patrick, you have 12 minutes, and I will give you a 2-minute warning.
Very well. Thank you, and I guess good morning from the United States here. I wish I could be in Greece, but this is, I guess, the next best thing. So I'm going to let me share my screen here. Okay, so I'm gonna. So hope can everyone see the screen here? Or hope. Yes. Okay, great. So I'm going to talk about a new project that we just received funding for a couple months ago, and so it's called Turbo, and it's a lot. There's a long title here, but so it's the Total Coverage Ultra Fast Response to Binary Mergers Observatory, so let me tell you about it. Our team here, it's I'm leading it at the University of Minnesota, and we have a large number of people in Minnesota who are part of it. And then we're partnering with University of Crete, so Vasilis and Kostas and John, and then New Mexico Tech, as well as Craig Wheeler at University of Texas, Austin. And so the idea will be that we're going to put a set of telescopes at Stenokos and then also at Magdalena Ridge, and I'll tell you more about that in a second here. So part of the motivation for this, the idea of Turbo, is that as everyone knows, LIGO and other gravitational wave observatories are currently, in most cases, only able to localize mergers within hundreds of square degrees on the sky, and even in the best case so far, which was gravitational 17017 event, in that case it took 11 hours for the optical counterpart to be discovered, and in the meantime we missed 11 hours of the evolution of the kilonova counterpart, leaving open some questions that earlier observations might have addressed, including what is the origin of the early blue component of the kilonova? Could it have been due to radioactive decay of our process elements, or perhaps shock heated debris? And the successful strategies here were going around and looking at nearby luminous galaxies, and that was successful. The other strategy is to tile the entire localization region, but current facilities, it takes, you have to slew and tile the whole region, and that can take quite a while. And so perhaps we're missing prompt emission. And so far, we only have, one or possibly two counterpart detections. And maybe that's partly because we're maybe missing prompt emission. The physical scale of these mergers is such that you could expect, of course, a prompt component, and you would, for example, expect that for the afterglow from a short GRB in the case of neutron star mergers. So there could be more exotic possibilities, of course, involving binary black holes or charged black holes, and some evidence for coincidence with prompt gamma ray emission, and perhaps in these accretion disks as well. So there's a possibility that we are missing some very prompt emission, and so it might be useful to follow up LIGO triggers very rapidly. And so that was the idea, and had this a few years ago, and had a couple of proposals, and fortunately is finally successful here. And so the idea is that original idea was we would, maybe cover up to 240 square degrees within 2 seconds. And so we have a prototype in St. Paul. So this is the University of Minnesota, in the Twin Cities. And so we have a St. Paul campus, which actually has a agricultural field for the agricultural school. And so we have a prototype telescope there. And here's an image we're able to take after getting, slewing across the sky, within 2 seconds after an alert. So the prototype seems to do what we want it to do. And we have many, in this version of the prototype, we have 4 telescopes, wide field telescopes on each mount. We subsequently are switching to maybe switching to 2 telescopes per mount, which have larger aperture, and in part because our camera manufacturer sort of has changed their plans a little bit. So in any case, here, let me show you the video of the prototype here. So this is what it's able to do. So it's a direct drive mount, which provides a lot of rapid acceleration, and but is also very precise. So it does what we would like it to do, which is exciting. All right, so let's see. Okay, so here's a prototype again in the winter. Minnesota's a good place to test whether systems work in the cold. So okay, so we're using this Roe Ackerman spectrograph from Celestion, they mentioned, and so one site will be at Skinnicos Observatory, and which is basically a world-class site, very dark skies, and has excellent seeing, and so we're working with Celestion and others to try to design the telescope enclosure at this point. And of course, the existing robotic facilities will be at the site will be terrific for follow-up. So we should be able to discover transients very rapidly, and then in our group here and outside of it, follow-up events. And so they'll be very exciting. So the other site will be Magdalena Ridge Observatory, which is near Socorro, New Mexico. So you can actually, I think, see, I've never been there, I'm hoping to go, see the VLA from the summit here. So this is at 10,000 feet. And there's this 2.4 meter, which is actually used to track missiles, I think, from the White Sands. So it's a very rapid slewing telescope. And so potentially we could use that to follow up within less than a minute transients. All right, so here's kind of a phase space diagram, and I think we may have to, given some of the difficulty with the camera manufacturer, maybe more like 150 square degrees. We're still trying to figure out some of the details here, but in any case, the idea is that we can potentially cover as far to our best of the understanding, and we may not be aware of every single project out there, but did our best here, and so have a lot more depth over a large area in a short time. And part of the advantage here is we have the telescopes on different mounts. We can actually dynamically resize the coverage area of turbo, of course, by pointing at either adjacent regions or the same. And so, there's a better localization, all the telescopes can be pointed at the same part of the sky, giving us additional depth. So that's the plan. And so that's the gravitational wave events. One of them is probably the main science case here, but there's a lot of other exciting science we can do, and which is fortunate because there's not always an active trigger at this point. So we're hoping to, for example, follow up neutrino triggers, perhaps from Gaia, as well as gamma ray bursts as well. And there may be all kinds of other things in addition to that. Okay, so another main science case is actually finding supernova explosions very early. And so there have been lots of exciting data in the last decade from especially Kepler and TESS. And so Kepler, of course, was designed as a planet finding mission. And so it has a very high cadence, 30-minute cadence. And so it's been able to find or observe supernovae very early. However, it wasn't able to actually discover them early and tell us on Earth that happened. Instead, there's so much data coming in, you had to tell it where to record the data, and then it was downloaded later. So we weren't able to discover supernovae at this cadence. We're only able to observe some subset of them. And nonetheless, they're very exciting observations. Here's 3 type 1a supernovae. Don't see evidence here for interaction with a companion. That's one of the big questions in type 1a supernovae. The study of type 1a supernovae. What are the companions of type 1a's? If you have a say a main sequence companion, in some fraction of the time you'd expect interaction, and they didn't see that for this sample. I mean, you really want more. And then Peter Garnovich has this paper where they, where he thought, and his collaborators thought, they found shock breakout of a type 2p. I think there's some debate in the literature about whether this could possibly just be an issue or just a statistical fluctuation. I don't know. It looks convincing to me, but I haven't delved into the details here. So anyway, that's something else. If you can detect shock breakout, you can study some of the constrain the size of the progenitor and access a new area of parameter space. The early light curves of a type 1a of core collapse supernovae are very interesting. They're not yet powered by radioactive decay, so their light curves are very simple and reflect and provide a way to constrain the size of the progenitor in a very direct manner. So TESS is currently operating in.
You have 2 minutes.
Okay. Thanks. And is sort of continuing what Kepler was doing. And so Turbo, we're hoping we have so many. We will have 4 mounts essentially at each site, or maybe possibly actually more. And so these will be used to observe nearby galaxies at a very high cadence. In fact, the cadence of shock breakout. So we should be able to detect a handful of supernovae at shock breakout hopefully every year. And we have the 2 sites around different sizes, so we have almost continuous coverage of the northern hemisphere if the weather is good. So the challenge then is to process all these data within it's something like the observing cadence, which will be a challenge. But we've put together a GPU-based pipeline, and we're using sort of machine learning to potentially do away with difference imaging as well, and for transient detection. And so we're anyway, this is going to be a challenge, but we're going to have a lot of GPUs, so hopefully that will work. So just to wrap this up, we're very excited. We recently received a grant from the National Science Foundation, the Major Research Instrumentation Program, and so our objective is to cover the entire localization region within 2 seconds for a high, some significant fraction of triggers. It appears that early predictions for the size of these localization regions may have been too optimistic, but some fraction will be, less than 150 square degrees, say, and then also find supernovae hopefully within tens of seconds or minutes of explosion. And we're currently have a couple engineering challenges, as you might expect, but we're making progress and hoping to construct the telescopes in the next couple of years. So thanks.
Sorry. Sorry. Thank you very much, Patrick. We have already a couple of questions. Does anyone from the audience wants to ask? No? Okay, so there are two questions on chat. Both are similar from Siegfried and Sumeda. I will just read the first, the Sumeda's question. I have the same question, sorry. Is your limiting magnitude sufficient to detect kilonova emission, or do you rely on hypothesized stronger prompt emission?
Well, sir, yes, I think we could easily say, for example, detect the counterpart of 1708-17 over, you know, I think it was, you know, 10 minutes or something like that. But I mean, obviously, the prompt response within, you know, a minute or something, we would be searching for something like, you know, an afterglow or something that's you know, brighter. But we would sit on the region for you know, hours or whatever. So we would build up a lot of signal to noise, you know, getting, you know, really, you know, I think 23rd magnitude, or it depends on the size of the region, of course. And the other advantage of turbo is that if we just sit on the region, right, we should see sources that are brightening on the time scale at, you know, after the merger, right? So that should help you know, identify good candidates versus, you know, otherwise you come back every couple hours, you know, you could be looking at old supernovae or something like that.
Okay, thank you very much, Patrick. I think we can move with the questions to chat or to Slack. There are already some follow-up questions for you waiting there. And now I would like to invite Magdalena Kunert-Bajraszewska. Magdalena, you have you have 12 minutes, and I will give you a 10-minute warning.
Okay. Okay. Can you see my slides?
No, we cannot.
No.
Just work. Are you sharing?
Yes, I'm sharing my screen now. Yes. No.
For some reason, we only see your face.
Okay. Sorry. Okay. Okay. Now should be fine.
Yes. Okay.
Yeah. Okay.
Yes.
Sorry about that. Okay. Welcome everyone. My name is Magdalena Kunert-Bajraszewska. I'm from Nicolaus Copernicus University in Torun, in Poland, and I would like to tell you about our project on slow radio transients. And I will start. Okay. Oh, yeah. Can you see the second slide?
Sorry. Yeah.
Yeah. Okay.
Yes.
So there's some delay. Okay, so I will start my talk with a plot showing the phase space of slow extragalactic transients. What you can see here, here on this axis, we have the radio flight. This is the number of detections or predictions of transient detections per square degree. The red line here indicates the source count from the previous large radio survey called FIRST. And you can see on this plot the number of this kind of surveys on slow radio transients is not small. Actually, this number shows that many of such surveys have been already carried out at a few different frequencies, but the detection of the slow radio transients is actually low. This is caused by the majority of limitations that had this previous surveys, like small field of view, for instance, low sensitivity, or sometimes only single epoch of observations. However, the recent scheduled and partially performed surveys on radio transients. Okay, another delay here. Well, I'm talking about these two transients which are placed in this corner of the plot. They have a better quality, so they have a much better sensitivity. And my talk, and my talk will be focused on these two surveys. Actually, on the first one, which is already finished. The second one, the VLA survey, is already ongoing, but I'm going to mention about the results from this survey also at the end of my talk. Both these surveys were performed with the VLA Very Large Light 27 antennas in New Mexico. Okay, so the CNSS survey. This was a dedicated survey for slow transient phenomena on timescales from 1 day to 1 year. It is already finished. It was performed between 2012 and 2015 with VLA at the central frequency of 3 gigahertz. There were 5 epochs of observations, and the noise level was really very low. So this source was up to 3 times as deep as the previous survey carried out on this part of the sky, the first survey. So as a result, different flaring phenomena, different variable sources, transient objects have been discovered, like flaring AGNs. This was mostly caused by the shocks in the jet in the AGNs that were known as radio loud before. But also candidates for tidal disruption events, for the stellar explosions, flare stars, and active binary star systems. However, also a distinct population of AGNs has been discovered. These AGNs were not detected as radio sources in any of the previous surveys of this part of the sky. And the hypothesis was that they are the newborn radio sources, so the sources that have that are only a few years old. They were detected at Millijansky level, and this was the sources in transition actually from the radio quiet to the radio loud state. The final sample consists of 12 such transient sources, and the goal of our project was to actually check whether this hypothesis is true. The hypothesis about the nature of these objects is true. So yes, the goals of our project: establish the evolutionary status of the discovered sources, and also to study the recorded phenomenon as the transition from the radio quiet to the radio loud mode, and take part in the long-standing discussion about what sparks the radio loud phase of AGNs actually. So is there a set of some boundary conditions that is needed to initiate the radioactivity in AGN, but also to study the changes that occur in the radio source and its host galaxy from the very beginning, from the first days of life, and study also the hypothesis that some of the transient objects may be short-lived phenomena or developing very slowly. Okay, so before I will go further and show you the results of our project, I would like to make a small digression here about the life cycle of AGN, because this is something which you already know about the radio sources, and it is and this scheme is actually already common and accepted. So we can, in the life cycle of radio loud AGN, we can distinguish some phases. Okay, and after the beginning of the radio emission, the radio structure of the source is very small. The radio source is completely contained within the host galaxy. The linear sizes are much slower than the 1 kiloparsecs. And the radio spectrum of this kind of objects is also very characteristic, because it peaks above 1 gigahertz, okay? And we call this stage and these objects GPS sources. With time, the source grows, develops structure, and and have extend their sizes to the size of the host galaxy actually. But also the radio spectrum changes a lot. The peaks move to the lower frequencies, and in the optically seen part of the spectrum, the spectrum is steep actually. So the phase is called compact steep spectrum. If the source is very powerful, it can grow further and extend the radio structure outside of the host galaxy and become an adult large-scale radio source with the sizes hundreds of kiloparsecs. However, there's a growing number of evidence that that majority of the radio loud AGN population can fade earlier, after less than 10 to 5 years. And this is especially, this hypothesis especially refers to the weak radio sources. But this is something which needs to be explored further also with the transient studies. Okay, so coming back to our sample of 12 objects. So the sample consists of 3 quasars, 8 galaxies, 1 source wasn't identified. Here you can have the SDSS coutouts of these objects, and we have also put them on the radioluminosity redshift plot to show that distribution comparing to the young radio loud AGNs, compact radio loud AGNs found in the literature. So as you can see, the 12 of our objects are weaker than the previous compact AGN studied so far, with the quasars being brighter than the galaxies. However, to study these sources and to correctly classify them, we had to plan some comprehensive follow-up observations. So what we did, when we did this, so we planned a multi-epoch and multi-frequency study in the very wide range of electromagnetic spectrum. So we planned radio observations, X-ray observations. We have also analyzed the infrared WISE data, the available SDSS data, and we had also some extra salt observations in the optical domain. I don't have time to go into details with all these results, observations, and analysis we did, so I will focus only on some of them, and mostly the radio observations. So from the high resolution VLBA observations, we can see that subjects are very, very compact. Some of them only were slightly resolved, and some small jets were visible in some of them. However, the linear sizes are really much, much less than the 1 kiloparsec. We have also a very nice set of observations of the radio spectra in a very wide range of frequencies and multi-epoch. There were multi-epoch observations. So we were able to follow the changes that happened in the source from the very beginning, from the very first days of their lives. So we can sum up this observation with this few conclusions here on the slide. So the spectra of all our objects peaking at a few gigahertz. So they have a typical, we say convex on an inverted shape of the radio spectrum. The radio spectra of the quasars evolve very rapidly, so we can observe changes in flux density, movement of the peak, and spectral flattening. Here is an example of such observations of one of our quasars. So after the GPS phase, we have observed in the first few months to even years in life of the quasars, the GPS quasar transformed into flat spectrum objects actually. And so this finding is important in the sense of classification and evolution studies of radio sources, because this means that some of the GPS quasars can be misclassified as flat spectrum sources and as old flat spectrum objects. Okay, in the case of galaxies, they behave in a different way. GPS and galaxies keep the convex shape of the spectrum during the few years of monitoring we have performed. So we can perform that all our sources have passed the GPS phase at the beginning of their evolution. However, the time dimension is different for quasars and for galaxies concerning this GPS phase. But what is also very important, the increase in radio emission or the ignition of radio emission we have observed in these objects is not just a single flare lasting a few months. But after this 3 years, even that we can observe some fluctuation in this the first part of the life of our objects. After this time, the radio flux stabilize at some level, so the source start to be let's say typical radio source. Okay, so I would like to distinguish one of our objects, because for this object we have.
Magda, you're almost out of time. 1 more minute.
Oh, that's bad. Okay, so I will try to speed up. Okay, so I would like to distinguish one of our quasars. Because for these objects we have a very nice set of observations. So okay, so I will speed up. This is a nice coordinate structure visible in VLBA observations. Again, GPS phase and then flattening of the radio spectrum. The source was discovered as a radio source at the end of 2013. But what we also observe for this object, because we have a nice photometric and spectroscopic recording, is that its transition to the radio loud mode coincides with the changes of its UV optical continuum. So this is the photometric recording. So this is the apparent magnitude. This is the time. So as you can see in the optical band, we can see some fluctuations and slow but statistical increase in the optical emission. Here are the limits from the previous radio emission of this object, and this is the date of the burst of radio emission. We have also a nice spectroscopic observations from the SDSS, and I will speed up this story to show that we also see changes in the level of the optical emission, of the level of the continuum UV optical continuum emission of this source, which coincides nicely. The high states coincides nicely with this GPS states, and then after 2 years, this optical emission come back to this previous states from the radio quiet phase. Okay. So I will skip this summary because I would like to give you some things, some thoughts, some conclusions at the end. Okay, as I said, the VILA survey is still ongoing. So we will have a few more, I think a much more discoveries of transition objects, and we have already choose another interesting sample to study in a similar way, and also comprehensive multi-frequency and multi-epoch observations. So there were these sources were undetected in the previous NVSS survey performed 25 years ago. Now they have a radio flux. They are detected as radio source with a flux more than a few millijansky. Okay, so some other future prospects which are related to this workshop are the possibility of the joint radio and optical searches for transients. The benefit seems to be obvious, so I listed at least some of them here. So the creating a database, improving the statistics of this phenomena, etc. However, I can also point out some conclusions and maybe probable conclusions from this previous surveys of the slow radio transients. So generally, the radio sky at frequencies of a few gigahertz appears to be quiet because the rate of slow transients are low. It's less than 1 transient per 10,000 persistent sources. So the fraction of transients among the persistent sources in the optical and radio scale is similar. However, we have, of course, a larger number of persistent optical sources per square degree. That implies that the number of varying optical sources is much larger than the number of varying radio sources. So generally, it is difficult to detect the slow radio transient. Okay, thus we need a deep radio observations. Deep means at microjansky level, even not millijansky, but also a deep multi-wavelength photometric and spectroscopic observations that is needed to classify it correctly, the transient object. So some maybe proposal for the future project and studies would be some follow-up observing program, for instance, with EVN telescope, telescopes with at Microjansky level for Gaia alerts. Okay, that's all. Thank you. Sorry for being too long.
Thank you very much, Magda. We are slightly short on time, so I would like us to move on to David Williams' talk. And if you have any questions for Magdalena, please ask them on chat or Zoom. David Williams, you have 12 minutes, and I will give you a 2 minutes to end warning.
Mm-hmm. Can you see my slides?
Yes, we can see them very well.
Right. Okay, hi everyone. First of all, thank you to the organisers for giving me the opportunity to talk today. I'm currently an operations support scientist at eMerlin in the UK, working with Rob Bezic, and I'm going to talk a little bit today about what you can already do in terms of rapid follow-up in the radio band for optical or any other sort of transient. This is based on partly on my work that I'm doing now as part of the support staff here, but also part of my previous work working with Rob Fender in Oxford. Now, a couple of things that have came up earlier in the week, which I think really sort of exemplified what I wanted to talk about in this talk anyway, that I heard in the discussions was how can we quickly follow up any sort of optical transient in the radio. You need to get time on a radio observatory, tell the schedulers, and then trigger, and then slew across, and that can sometimes take a couple of days or a week if you're having to write a DDT. And how else can the radio band help my science as well? So we've got a new optical transient, for example. What can we do more than just imaging? Are we just looking for a noise limit in the radio, or can we do something else with it? Now, I'm going to talk mostly today about the first question, but the second question, you can do some extra bits and pieces, like, for example, in the Milky Way, if you observe at 1400 megahertz, you can look at the H1 line, and that can give you an idea of the distance to, say, a source. So we use this sometimes for X-ray binaries to get an idea or a limiting position on the distance of a source. But I'm going to talk mostly about rapid follow-up of transients today. And to do that, I'm going to talk through 3 telescopes that I've used quite extensively over the last few years. That is eMerlin, where I work, the AMI Large Array, which you can see in the middle there, and the Meerkat telescope, which many of you will already be familiar with. Now, I've listed here some radio interferometry jargon, but the main things that I want you to take from each of these telescopes, or the main conclusions that I want you to be thinking about throughout this talk, I've listed in white at the bottom. So the eMerlin telescope is situated throughout the UK, from Cambridge all the way up to where I am here in Cheshire. These long baselines give us sub-arc second resolution. And it's this high resolution which is incredibly important, incredibly useful if you want to discriminate your source from another source in a very crowded optical field, for example, X-ray field. The AMI array, which many of you may or may not be familiar with, is based in Cambridge at MRAO. And it has a much poorer resolution because, as you can see from the picture, the telescopes are quite close together. But we have, as part of the program in Oxford, had a robotic follow-up mode running on the telescope for the best part of a decade now. And I'm going to talk a bit about that in a second. And then finally, the Meerkat telescope, which has about a 5 arc second resolution, so in between these other 2 arrays. But as part of the Thundercat large survey program on Meerkat, I'm involved in following up radio transients, but also other types of transients like gamma ray bursts and X-ray binaries on a weekly basis as part of the regular Thundercat monitoring. And the best way to go through this is to give you an example of a science program where pretty much these three telescopes working together enabled us to do a whole range of science, and that is this source here. I've listed it by 3 different names, but I'm going to call it Maxi J1820 throughout this. This was a source that was detected in March 2018, and it was first discovered in the optical by Assassin, but on the right-hand side, I'm showing the Gaia alerts page optical light curves. You can see at the beginning of 2018, it had a 5 or so magnitude optical outburst. It wasn't until a week later that it was detected in the X-rays, and this is something that I'm keen to sort of stress, is that when we're looking at some of these energetic phenomena, we're waiting for an X-ray trigger of some sort. But if you've got an optical trigger and it's robust, then why not trigger the radio as well? So far, we've been, this source was classified very quickly as an X-ray binary. But if we had known a week earlier about this new source, we could have had a week's worth of extra observations. In fact, it was so bright in the X-rays that it triggered the Swift BAT monitor. And that's when we started the radio observations. Now, all the following work I'm about to present is work that has been done by Joe Bright in a Nature Astronomy paper last year that I've worked on with him in reducing some of the data. So you can find about all of this source in the radio observations for it. So the first thing I should mention is that, as I said, we got a trigger from the X-ray Swift BAT monitor. Now, the Swift BAT monitor, once any astrophysical transient gets above a certain X-ray flux, it will send out a VO events, and we will take that information. And as of from about 2013 or so, we've been taking that information and feeding it straight into the AMI large array as a robotic follow-up mode. So whenever one of these triggers goes off, and this is usually for a gamma ray burst, for example, but we can also follow up at X-ray binaries when they get bright enough, as in the case of J1820 here, or radio follow-up from a gamma ray flare from DGCVN, we can be on source really quickly. So the example I give is on the right here. You can see that the first 3 radio data points here in red are from AMI, and they are all within the first 2 days of the initial detection of the gamma ray burst. In blue is the first VLA data point after about 2 days after, but without those initial three AMI data points, you wouldn't have been able to characterize this bump in the light curve, which is the reverse shock emission from the gamma ray burst. And this has proved to be really, really hard to find in the past, but being able to robotically trigger AMI on these sorts of sources means we can really, really quickly get detections for that really early, very rapid variable behavior. And I should say this in principle can be edited to include other triggers from other places as well. So at the moment we just trigger off Swift, but we could in theory trigger off Gaia as well. So as I mentioned, J1820 we triggered off the BAT, and on the left here I'm showing some of those radio observations. Because we were able to observe very regularly with AMI, we were able to detect this strong radio flare in one of the observations. And actually what you can do with this data is you don't even have to image it at these levels. You can take your voltage data, average it down into 30-second, minute-long intervals, and it gives you this very, very neat, rapid sort of flaring behavior, which is quite nice to see in these few-hour epochs, for example. Because the radio and the X-ray were able to observe simultaneously or quasi-simultaneously, we're able to build up what we know in the X-ray binary field as the radio X-ray plot. So radio on the y-axis, luminosity, and X-ray on the x-axis. And what we saw with AMI is radio emission throughout the outburst on this source. And normally, for those of you who don't study X-ray binaries very often, Normally, we only see radio emission from the compact central component when the source is going along this track here, and called sort of like the radio, the universal sort of track for X-ray binaries when they're in what we call the hard state. But we actually saw radio emission from this source when it was in the soft state, and that's when we think that the central component should have quenched its radio emission entirely. And because of that, something weird's going on. And what you need here really is the high resolution to disentangle what's actually going on underneath it all. And that's where eMerlin steps in. So as I mentioned earlier, you can get sub-arc second imaging. In fact, at 5 gigahertz, you can get down to 50 milliarc seconds with eMerlin, which is really, really nice and comparable to things like the HST, maybe slightly better. And because eMerlin is dynamically scheduled, so I'm one of the schedulers for eMerlin. If somebody sent in a DDT, for example, one evening, the next morning, myself, one of the other schedulers will look through all of our programs and decide what's the best thing to observe that day. And we were able to, in the case of this program, get onto the source within a few days after this radio flare that we saw with Amy, which is really, really nice. And what we actually saw, I don't know how clear it is that is there in your screens, but there's actually two components, one which is a fading core component and one which is a discrete piece of ejector moving away from the black hole. And we were able to track this over 3 weeks, moving gradually away from the black hole. And this puts really strong constraints on the time frame of the ejection and allows us to link it back to that initial flare that we saw with the Amy data. On the right hand side here, you can see I've
Sorry, you have 2 more minutes.
Yep, you can see I blocked out part of the plot here, and on the top is the separation of this component moving away from the central where the black hole would be over time. And these are the constraints from eMerlin, but you need the long-term monitoring. And that's what I'm showing here with the rest of the plot. And by doing this with various different observatories like MeerKAT, also the VLA and VLBA here, we're able to fit different models like a linear or a constant deceleration model to this ejector, which tells us about the physics of that ejector. To conclude all of this, I think it's really important that you have to bring all of this together as one sort of overall program. And so this is what I'm displaying here, that the early radio follow-up gives us that radio flare. The high resolution with eMerlin then allows us to give strong constraints and link the component to when it was ejected and subsequently moving away. The long-term monitoring allows us to see these flux variability and movements of the components. By looking at the movement of the components and fitting these models, using simple geometry, we can actually then get an independent estimate on things like the distance to the source. You can also do a trick where if you observe at the same frequency, but with 2 different resolutions at 2 different arrays, it also tells you something about the emitting region of that source, that ejector that's moving away. And that can tell you about the energy that has gone into that ejection in the first place. And you can see this is all summed up on the right-hand side here by the 200 days worth of radio monitoring from eMerlin through to MeerKAT and the ejector that we observed moving away from the central black hole component. So I'm going to finish here. I'm leaving this as my final slide because if you're interested in getting sort of looking into observing in the radio with your optical sources or any other transient source, some of these programs already exist. So, for example, Amy, the alarm trigger robotic follow-up mechanism is run by Rob Fender at Oxford, and possibly we could link that into other optical streams in the future. And things like eMerlin with developing new rapid response triggers to allow us to get on source even quicker. So like i.e. in less than a day, so that you can really start to follow up the really early variable emission from these interesting transient sources. So I think I'll leave it there. Thank you.
Thank you very much, David. I think we have time for one question. Is there anyone? I'll check the chat. No. Okay, maybe some of them will come in time later on. If that's okay. Okay, so if you have a question, we'll be moving on. But if you have a question, post it either on Slack or on Zoom in the chat. And now I would like to invite Elena Szablowińska to have 12 minutes, and I will give you a 2-minute warning.
Okay.
You can start.
Everything is okay? Everything is seen?
Yes, we see your slides.
Okay, thank you.
And we hear you.
So I'm going to talk a little bit about the new abilities of the Agn monitoring in optical band that we did in our Special Astrophysical Observatory with a pretty big collaboration of different quarters. And so I would like to start with a little bit historical overview of what we are doing here. Actually, all this project was started more than 30 years ago, and all is about the Agn monitoring, all is about the monitoring of the internal parts of the central parsec of the AGNs, where the supermassive black hole accretes the matter, where the broadline region is, the inner part of the dusty torus, and all this we are investigating by really various different methods. All this we called like magic, monitoring of active galaxies by investigation of their cores, only previous year, but our project is really very long. And it was started by two very outstanding persons, Dr. Alla Shapovalova and Dr. Viktor Afanasyev, who unfortunately passed away previous years. But all these investigations are really time domain, except this one, except the spectropolarimetry of type 1 AGNs. So I'm going to overview a bit all these different types of observations that we are doing. And first of all, that the spectral monitoring of observed galaxies, such a classical type of investigation of observed galaxies that we are doing. And as you can see here, for many years, for about 20 years of monitoring of such type of galaxies, we can see the variabilities not only in brightness of the object, but also in the profiles of the emission line. And when we are investigating such kind of the emission lines, which are produced in the central parts of the active nucleus in clouds that are photoionized by the accretion disk, then we can trace the motions of these clouds in the broadline region. And because the broadline region cannot be resolved, because of this very intensive monitoring, we can analyze the profiles of these lines and trace the virial and non-virial motions of the matter inside. Also, we can locate the sources of different lines, of different emission lines, the Balmer lines, the Ferrum lines, the other sources, and also, which is very popular right now, we can investigate the nature of the so-called changing look AGN phenomena, when the broad line one moment disappears from the spectrum. All this about the individual galaxies, but also tracing the very large number of such galaxies, we could also obtain the time delay of the broadline emission relatively to the continuous spectrum. And that lies in the idea, in the basement of the idea of such called the method as reverberation mapping. The idea was firstly initiated about 50 years ago, actually, but right now it's still very modern and still is very up to date. So when we obtain the time delay of the broadline region emission, then we trace and determine the size of this broadline region in its location in the central parsec of AGN, which is again unresolved. And having this size of the broadline region and the velocities from the emission line, we can obtain the supermassive black hole masses. And we are doing it in such kind of photometric approach, not with the spectra, but the photometric data in the medium band filters, covering the emission line and covering the continuum. We are doing it right now in a very young team, and we investigating in such kind the supermassive black hole masses. And also all this is for such kind of the relation that's called radius luminosity relation, the radius of the broadline region and the luminosity of the whole AGN. And as you can see here on this plot, there are plenty of such kind of plots actually, but here you see that the radius of the broadline region depends on the luminosity of the central core. And having such kind of relation plotted with lots of different galaxies, then we could solve the statistical problem of how to determine supermassive black hole masses from only one observations. Especially it's important for the very far galaxies. Also, we could change our idea of the photometric reverberation mapping to the next step, to the polarimetric reverberation mapping. And here, a couple of words about the polarization in the AGN, which I am actually specialized in. Actually, there are lots of different mechanisms in the AGN of how to make the emission really polarized. That's about the accretion disk, the synchrotron emission from the jet, different scatterings in the hot corona of the accretion disk, for example. But here also is very important two mechanisms of the scattering, the equatorial scattering and the polar scattering, that also traces the dichotomy of Syrphid 1 and Syrphid 2 galaxies because of the orientation of the polarization relatively to the radio axis of the galaxies. And we are interested in such type of equatorial scattering that is because of the scattering of the inner part of the dusty torus. And as it was shown about 6 or 5 years ago, when we are tracing the velocity, when we're tracing the polarization along the very broad emission line, and because this broad line region is such kind of a disk that is differentially rotating, that's why the polarization along the broad emission line actually change. And here on the spectra on very famous Mercury N6 galaxy, you can see that really in the places of H alpha and H beta lines, here are the different parameters of the polarization that changes along the continuum. And the main feature is here the S-shaped profile. And tracing these velocities with this polarization angle, we can obtain the mass of the supermassive black hole by only one measurement. That's very important and very useful tool. But here you can see that one specific feature, one specific characteristics we need about the AGN, the size of the scattering region. And actually the question is, if we are determine this size of the scattering region correctly, usually we can do it with the infrared measurements, but is this infrared measurements also about the scattering region that we are dealing with in this type of observations? So that's why we introduced such kind of the method as the polarimetric reverberation mapping, the reverberation mapping in polarized light. To be honest, it was done firstly 10 years ago. Then Martin Gaskell initiated such kind of observation, such kind of idea, but they didn't succeed because they were dealing with their broadbands where lots of mechanisms, polarization are mixed up, and that's why this try wasn't really very successful. We decided to go to obtain such kind of the polarimetric observations in the very medium bands. And that's why we are covering exactly the emission from the broadline region, which is totally unpolarized. And it's the same emission from the scattering of the dusty torus. And that is polarized only due to the one mechanisms. So that's why we are obtaining such kind of the scattering radius, which is greater than the radius from the optical reverberation mapping and is smaller than from the infrared observations, actually. The observational tests was done also for Mercury N6 galaxy again. And if for this galaxy, the previous observations showed that there is a very small polarized continuum region about the 2 days, that's about the size of the accretion disk. The size of the broadline region is about 20 days, but here we can see that the size of the equatorial scattering region is about 100 days actually. And it's in very good agreement with the theoretical predictions of the sublimation, of the dust sublimation radius. and is 2 times less than what we are having from the infrared interferometric observations. And actually, the preferable scenario of why there is such a big difference is because the maximum of the brightness temperature in the near infrared band is not equal to the dust sublimation radius in the AGNs. So we now are initiated such kind of different methods of testing the inner structures of the AGNs. And that's why we are doing such kind of monitoring in the narrow band, medium band filters with the polarimetry, because the spectropolarimetry is actually the more useful tool, but to have such kind of spectropolarimetric monitoring, you need very big telescope and you need very big amount of time. So we are doing such kind of observations now on the pretty big collaboration of different small telescopes. This project is ongoing. So I'm going to the different types of polarization, actually, the variations of polarization.
Elena, you have 2 more minutes.
Yeah, okay, so I'll be a little bit faster. So for the broad line, for the blazars objects, when you see the inner structure of the jet, the polarization is actually crucial. And when we did the continuous 9-hour monitoring, we see that we can trace the plasma motions inside the jet. So this tool could be very helpful and could trace the motions inside the jet, and so to determine the structure of the inner jet on the scales of the 1/100th of the parsec from the supermassive black hole. So all this task we are now doing on the 1 meter telescope, and especially for our issues, we constructed firstly in 2020, in the beginning of 2020, the very simple device named Stokes polarimeter with only 2 modes, the photometrical and polarimetric one. And very successfully, we operated it for about half a year, but then we decided then these types of errors, this types of device is too simple for us. And that's why previous year, 1 year ago, we constructed this device named MAGIC, along the name of the project, which is the focal reducer with 3 modes, direct images, spectroscopy, and polarimetry with such a type of a quadruple Wollaston prism, which give a very big field of view, about 6 by 6 arc minutes. So here are some errors and characteristics of this device. So here you can see that with the focal reducer on the 1 meter telescope, we could do it really efficient one telescope. And in the very beginning, the bright picture of the Crete Nebula and the polarization of Crete Nebula that we did as a test for such kind of observations. So thank you, and I'm looking for your questions.
We are short on time, so I would like to. I want the people who have questions to ask them on chat or on Zoom, on Slack. And now I invite Mariusz Gromadzki to give a talk on Ogle survey, extragalactic transients. Mariusz, you have 12 minutes, and I will give you a 2-minute warning. Mariusz, are you talking? Because we can't hear you. Mariusz?
Sorry, yes. You should
okay,
hear.
Thank you.
Okay, do you see my slides, I suspect?
Yes, and we hear you.
Hi. So I'm postdoc hired by ORP at Warsaw University, and I mostly work on the spectroscopic follow-up and classification of the transient in various collaborations like IPESTO, and I work also with David Buckley using the SALT, the spectroscopic classification and follow-up of the various transient. I am also involved in the Ogle project, and Łukasz asked me to say a little bit about this project. This project was established in the beginning of 90s, like the other microlensing search project, Eros and Macho, but this is the one which survived the 90s until pandemia. and it starts in the SWAP telescopes. In 1996, there was the built by Warsaw University own telescopes 1.3 meters, and there is the upgrade of camera, of course, and the other upgrade of camera was in 2001, and from 2010 we have the 4th edition of the OGEL project, which was stopped by pandemic. From the beginning, project was led by Andrzej Udalski, and Andrzej Udalski got the funds to restart the OGEL, and it will be restarted as a 5th edition. OGEL is a pioneer in using of the differential image analysis, and with the 4th edition, we got the bigger camera. In this time was the third biggest camera in the world, I think, and it contains 32 chips, E2V, and it's cover 1.4 square degree. With new camera, the field of view not concentrate only the denser region of the center of the galaxy and the centers of the Magellanic Clouds, but the coverage was significantly expand. And despite of the central region, we start to cover the galactic plane, and also we cover the huge area around the Magellanic Clouds. Looking for we start to collect the data for the galactic plane, and despite of the microlensing events during this almost 30 years, OGEL provide fantastic time series for the almost all stars till to 20. Depends on the region. We use the different exposure time. And we provide the excellent time series for the various objects. And we also start from 2010 looking for the extragalactic transient in the region of the towards the Magellanic Clouds. And here you have the examples how it works. We collect the data points for the same region more or less every three days. And at the beginning of the project, the template image was made, which is subtract from the current image. Here you have the template, then you have the current observation, and you have the difference of two of them. If appears the some new object, it's easily detected on the difference image, and it works perfectly in the empty field. But you see that in case of the galaxy, it works also very well. Even in very difficult to observation central region of the galaxies, it also provides reliable detection. And during the years, it's just simplification, because the Magellanic Clouds are observed from from the September to the May, and during this slightly more than half a year, we are able we usually discover around 120 transients, and the first 2 years was summarized in the paper written by Szymon Kozłowski, and the next 2 years from 12 to 14 was summarized by Łukasz. Okay, I just show you some highlights discovered by our research. I think that the most impressive object is the OGEL 16AA. This is the first transient discovered in the year 2016 by Łukasz after New Year Eve, and this is the tidal disruption events, and this is the I-band light curve, which is quite unusual for the tidal disruption events. It shows two maxima, and follow-up and classification spectra confirm that is the tidal disruption events. It shows the very hot continuum and very broad helium lines. And here you have the subtraction of the continuum, and you see the helium line is very broad, and you see some traces of the very broad H-alpha. This narrow components most likely comes from the host. And And the other event is also the nuclear one, which is one of the first Bowen flare of the central black hole. And here you have the I-band light curve, and in spite of that is the follow-up made by Swift, and you see the light curve from the Swift. This is the temperature evolution. Object at the maximum was very hot, and then the temperature decreased to 20,000, and it became more stable during the all-time evolution. And here you have the spectroscopic evolution of the object. Object is the middle spectrum. It's obtained 10 days after the maximum, and you see the very apparent emission of the helium-2 plus this one is the emission from nitrogen-3, and this is quite similar to the other object which was discovered by Tad Hunter, but it was wrongly identified as a tidal disruption event. And this is the comparison with canonical tidal disruption events Assassin 14 Li, which looks completely different, and the other spectra shows the slow evolution of this object. Okay, because this conference is about the Gaia things, it worth to mention how about the synergy about these two surveys, because this is very hard to design the survey which is self-efficient, and you usually need the collaboration with the other surveys because of the weather. Of course, the Gaia is the space mission and is the weather independent, but anyway, you have the different issues with with the cosmic mission. And here we have the one of the supernovae which I will currently work on, and here we have the OGLE data 50 days before the maximum, and in this moment we have the seasonal gap, and we cannot get the other observation, but fortunately Gaia can observe slightly longer, and thanks to that we got the additional points, and we have some estimation about the decline rates of the object. And after when the object back to the sky, it was not detected. And here you have the spectral evolution of this object using the SALT and NTT. Okay, and the other object, Gaia 2000 FKK, it was discovered by Gaia. Here you have the Gaia light curve. It is in the Large Magellanic Clouds, and it shows some increase of the magnitude, about half a magnitude. And at the beginning, we thought that this could be a stellar merger in the Magellanic Clouds, but then the object back to its previous brightness, and it's continue in about 16.5 magnitudes. And we got the spectrum using the SALT, and it shows the cool star continuum. It's about K giant plus very narrow Balmer lines and helium-1 lines. This object fortunately was observed by OGLE during third phase. During the fourth phase, it's located between the chips, so it was just sporadical points for the phase 4. But in the case of the first 3, the coverage was very good, and thanks to that we can model we can see the light curve, and we find that this object is the ellipsoidal pair of the two giants, which with period about 230 days. And despite of the regular operation of the OGLE, from time to time, actually 2 times till now, we together with our Chilean collaborators, we ask for the 2 weeks to looking for the very fast transient, and we choose the region between the Magellanic Clouds and the galactic. This is shown here, and we try to find this transient online, and many people works during the night just to looking for the transient, check to the light curves and check to the alert. And here we have some examples discovered in 2018. We have two sessions, 2018 and 2019. During 2018, we discover 4 transient during the session. Next year, we don't discover any transient. Okay, this is all what I would like to say. I hope that I fit the time well. So I hope that the pandemic was finished more or less soon, and we can back with the 5th. We can physically go to the Las Campanas and restart the project. Thanks.
Thank you very much, Mariusz. Do you have questions for Mariusz? We have a little bit of time. Okay, I will ask one question. Mariusz, what is the most common type of transients that Ogul detects in those fields? And are there any very interesting classes that you didn't suspect?
This is quite common for all surveys, and this is the supernovae 1A, because they are bright.
Yes.
They are -19 and.
Siegfried, you have a question?
Yes, you showed the light curve from an event in the Large Magellanic Cloud.
Yes.
With a very special light curve shape. How can it be explained?
I have no idea yet.
Yes.
This is some kind of the interaction between maybe some accretion episode, but the lines are very narrow, so I'm not sure. We are used to that the accretion events produce the broader lines. Maybe some magnetic field involved in that. I have no idea yet.
Very intriguing.
Okay, Michel, you also have one question?
No, but it's just a comment on what was said before. The narrow emission lines you see there are probably just due to the gas which is surrounding it. There is gas everywhere in the Magellanic Cloud. And wherever you point your spectrum, you find H alpha, H beta.
No, Michel, we take few spectra. I don't show that, but we clearly see the evolution.
Oh, yeah, okay.
Okay, thank you very much. Now I would like to invite Nada Ihanes. Nada, you have 12 minutes, and I will wave at you when you have 2 minutes left, okay?
Okay.
Yes, please share your slides.
Yeah, I just done it like first. Okay. Yes. Okay. Hello, everyone. I'm Nada Ihanes, and I'm a PhD student at Astronomical Observatory, University of Warsaw. So today I will be talking about the mystery behind the high amplitude AGN variability. So we've heard about some talks today about the AGNs already, but so the typical AGN variability in optical bands is a few percent of magnitude. However, in the recent years, the all-sky surveys started to detect big changes, more than 1 magnitude changes in AGN. So not only that these changes are visible in optical, there are also changes in also spectral changes. So this does not really support the universal unified model, which was also mentioned yesterday. So mechanism behind those changes are still unknown. However, some possible interpretations could be that this variability or these flares occur because of the supernova explosions inside of the, well, close to the disk, or tidal disruption events, changing loop quasars, and then changes in accretion disk itself, or even potential microlensing events. And here, by microlensing, I mean the lens is either in our halo or somewhere in between our galaxy and the AGN. So what I wanted to do was to see the AGN, so this low variability in Gaia alerts. So far, Gaia has detected more than 80,000 alerts, and since 2019, it got really like we started to see a lot more variability, so AGN, because of the introduction of the new detector, the Supernova, which you've heard about. So I was interested in the slow variable, so the variable AGNs with big flares. So the cuts I've done was to first just the alerts that were not detected in the galactic plane. Then I've checked all the under the classification, the ones that are classified as AGN or quasars. And then under the common, so the ones that were unknown classes, I checked that it said either the candidate quasars, candidate AGNs, or I was looking at the rise of or decline. And all of those magnitudes, for the amplitude, I decided to do that it has to be more than 0.5 magnitudes. So on top of this, so on top of the cuts and the actual light curves, I am checking also the archival data, so the Catalina measurements, and also if there are any archival spectra, this which could help explain what's happening. So on the right, you can see two of the examples of the light curve that are what I'm searching for. So on the top, you see there were some variability in the beginning, and then this one has been slowly but steadily increasing for the last, I think, few years. And then on the bottom, you have a sudden, fairly sudden increase by more than two magnitude in the light curve. I decided, well, not I decided, but I am not interested for this study. The light curves as are shown here, so they are both known AGNs, and they have high variability, but like I said, I'm interested in slow variable in the baseline, and then all of a sudden you have increase. So I've only started this spectroscopic study. So I haven't done I haven't observed a lot of targets, but I have few examples anyway. So one of them is Gaia 19XP. So this was alerted in 2019. It did have small variability even in Gaia, and when we checked the Catalina data, Catalina observed this from 2005 to 2013, there's also no previous flares in the detected. So we saw there was one magnitude rise in the quasar. So the archival spectra showed that the host is the narrow line Seyfert 1 galaxy. So we got the classification spectra, and in the classification spectra, there were visible this bone fluorescence, which Mariusz also mentioned before. So with what happens in the bone fluorescence flares, there is a sudden increase in UV optical emission, and this enhances the helium-2 Lyman alpha line and initiates the bone fluorescence cadence, which is extremely visible and extremely strong in helium-2, nitrogen-3, and oxygen-3 lines. The origin of this UV emission is most probably in the broad line regions, and once the UV emission disappears, the bone fluorescence settles back. And this was actually observed also in this target. We've done more than a year, now almost 2 years of spectroscopic follow-up. And as you can see on the right, towards around the peak, you have strong both nitrogen-3 and helium-2 emission, and then at the 103 days, so after the peak, the bone emission becomes to disappear. The next one that I would like to talk about is the Gaia 19CQ. So this was also alerted in 2019, and it had 1.3 magnitude rise in 1 year in a known in a known quasar or AGN. Sorry. So it did have some lower Catalina variability in the past, and there was also SDSS spectrum. So the interesting part here was that the spectrum is more or less featureless, and the redshift provided was 0.7. However, I'm not sure based on what this redshift was measured, because when we observed obtained the spectrum for just the optical part, which is from like around here 4,000 to the left, we weren't able to determine any prominent features and to see if what is the redshift and what type of event this was. Only when we obtained infrared spectrum from fire, it was visible that the H alpha was actually in the infrared, and the redshift was 1.6 and not 0.7. So this is the comparison of the spectrum, the archival spectrum in red, and then in black the combined optical and infrared spectrum. The quasar is low ionization broad absorption line quasar, and it's extremely blue. And as you can see, you see also the broad line regions are around more than 50,000 kilometers per second. Then there are two more targets for which I have spectrum. So on top, Gaia 20 AHA, there was small prior variability before the beginning of the rise, and the spectrum was obtained shortly after the detection. This turned out to be normal AGN. It has extremely broad lines, around more than 10,000 kilometers per second, and really strong neon, so forbidden neon 5 line. But other than that, it's normal AGN. And then we have the Gaia 20 BTE. Again, normal broad line AGN with strong magnesium 2 lines. So for now, the spectroscopic follow-up or spectroscopic classification of these candidates is ongoing, and currently, due to the volcano eruption in La Palma, the INT is not operational from where I was getting most of the spectra. So we'll see what happens. And to finish off, so in recent years, there were big amount of this kind of peculiar objects, and the problem is that it's extremely challenging to find good model and mechanism behind these changes. So we need more data and more transients, and Gaia is a great tool to discover them. And I'm looking forward to seeing the new transients and see what the old ones are doing. And that's it.
Thank you, Nada, for a nice presentation. Do we have questions for Nada? Łukasz?
So the 1962, the spectrum we got was very soon after it was alerted, right? But then it was 2 years ago. Is there any chance we could see what happens, at least in the optical part?
Yes, so for optical part, we do have follow-up from NTT.
You mean more spectra?
There is more spectra. It would be good to get new infrared if possible, sure. But yeah.
But the event, it keeps fading, but it hasn't faded yet.
Yeah, it's extremely slowly fading. Yeah. I didn't show the updated light curve, but it's still ongoing. I think it's still I think around 18.6 or 18.7 magnitude.
Okay.
So yeah, it's extremely long.
Cool.
Just a little comment. In the R3, there will be a list of QSO that will be published, which is a merging from different CUs, and these lists are reaching billions. those which variability detection was detected, there will be the time series.
That's great.
But the classification of those is based on only Gaia data, right? So the variability, but also BVNRP spectra, I guess, the motions and all those, not spectroscopy.
No.
Yeah. So what here I'm focusing for those from optical light curve. Based on the optical light curve, I try to get the I observe in spectroscopy to try to see what's happening there, because this is the
that's what should be done.
Yeah. So, but still, great.
I will allow myself one question and another. How big is your target sample? So the sample with your objects that you want to analyze?
Well, for right now, because it depends on right now I'm working with, I hope to get around 30 spectra, so 30 targets, but I have a lot more targets. It's just the issue of getting time on telescope. So.
Okay, thank you. Okay, so now, Łukasz, will you turn off YouTube?
Yes.
Thank you.
So I have to say sorry, I show my face. I have to say goodbye to our YouTube listeners, and so I'm stopping the stream because there's going to be some secret stuff being shown in the next two talks. So thank you for watching us on YouTube, and stop this.